Hello, everyone.
There we are.
Hello.
Hey.
Okay, I'm trying to make sure that the message is not shown. Okay, good.
Good morning. Well, morning. Yes, morning to you.
Hi, everyone.
Yeah. Morning, everyone.
Hi, good morning. Good to see you. So we started this half an hour early because we just wanted to get the room open. But the program doesn't start for another half hour. So
it doesn't matter. I think there's also a few things to discuss between us, but don't worry. Maybe you want to stop the recording and start it right before or something.
I think I can pause it.
Great. Let me try to share my screen. Here we go. Okay. So welcome, everybody. My name is Margarita Chli, and this is our ICRA workshop on robust perception for autonomous field robots in challenging environments. On behalf of all of the organizers, I'm welcoming you to this workshop. Good morning and good afternoon. Good afternoon from Zurich. So just to present briefly the co-organizers, if I manage to stay on the correct slide. So this is a joint effort together with Chris and Andrew from CU Boulder, Ali Aga from NASA JPL and Caltech, Kostas from Norwegian University of Science and Technology, Luca from MIT, and myself. So we have split our agenda in 3 different sessions, basically. We came up with, hopefully you agree, a set of very, very good talks. So for this morning session, we have Davide, CJ, and Sebastian. At the end, we have the opportunity to take some questions from you. It's a panel discussion across the 3 speakers. There is in this Zoom link, you can wave your mouse and find the Q&A functionality where you can type your question while you're watching the talks, and we get to select the most interesting representative ones to be answered. Afterwards, there will be a poster session, which I am asked to inform you there is a separate Zoom link for this. You will be reminded, though, at the end of the panel session anyway. The agenda and the Zoom links you can find always on our webpage. Then we have a brief lunch break, continuing with 3 more talks and a panel discussion with Jeanette, Claire, and Larry. And finally, we have Sanjeev and Tim for the last 2 talks for the day, and a panel discussion and some closing remarks. Maybe a few things to note. Of course, the meeting is recorded. I guess you all realize that. Now, the main reason that we came up with this workshop is because we all work in this area, robust perception, and we approach the problem from different perspectives. And the main purpose of the workshop is to see also some other perspectives and bring up some good discussions, which hopefully lead to interesting problems, interesting ideas. And hopefully also this would help us pursue a special issue at the journal. So this is still something that we are thinking about, but we have high hopes that this will result in one of these. Yes, so basically this is all from my side, brief opening remarks. So we are looking forward to see the new developments that people have, our star speakers have. So we'll stop sharing my screen. And then maybe Davide, you can start. Costa, you want to take the word?
Sure. Just welcome from my side also. And I'll just take the word to introduce Davide, and then Davide goes ahead and starts the workshop officially. So our first talk is Davide Scaramuza, professor at the University of Zurich. And the talk title is about robust and agile perception for micro-air vehicles. So we are all excited, Davide. Please go ahead, share your screen, and let us see what you will present.
Thanks, guys. Okay. Okay, I'm sharing my screen. So, good morning, good afternoon, good evening, everyone. I'm Davide Scaramuzza, and I lead the Robotics and Perception Group. Today, I would like to discuss actually the most recent works that we have been doing, not only on drones, but also on robust perception for cars. So I added this part as well. So let me start with cars first, and then I will talk about micro aerial vehicles, okay? So there have been a lot of new data sets over the past 3-4 years. So here are some images from the new scenes data set from Newtonomy. And I think what robust perception is about making algorithms that can cope with difficult scenarios, which actually represent only the smallest percentage of all possible scenarios. So what we call as corner cases. So what I want to show you here in these few slides are a few corner cases that we have identified in the current automotive data sets. So as you can see, New Scenes has several scenarios where there is both low illumination as well as the sun in the field of view of the camera. These are scenarios that typically happen, for example, during sunrise, dusk, and dawn, where basically the sun is at a very low sun angle. And currently, all autonomous cars have a problem with. So I actually want to witness, I could witness this myself, because the last time I was in California, I went for a test drive with Waymo, and actually the car had a lot of problems driving by itself because of the sun basically causing the cameras to saturate. These are actually also images from another dataset, the Waymo dataset. And here you can see what happens, for example, when the sunlight is in the field of view of the camera, you can't actually see in some frames the light of the traffic light, unless you actually sacrifice a little bit of exposure time, like in the bottom row. Here you can see again another Waymo sequence. Here we have both HDR, low light, and also rain. So these are actually very difficult for standard cameras to see. And here again, another HDR data set of Waymo, where actually you can see, especially in the bottom row, that actually most of the pixels are washed out. So here also another data set, this time from China, from Tsinghua University and SenseTime, and again, same problem occurs. This problem occurs both with global shutter cameras and rolling shutter cameras. So at the moment, what actually we have identified is that many algorithms actually intentionally avoid these scenarios. So, of course, there have been many sensors that have been proposed to tackle these scenarios. And we just added a new data set to the catalog of all possible driving data sets. And we call this new data set DSEC. It's a stereo event camera data set for driving scenarios that was just published in the letters. Let me show you a few sequences from the DSEC data set. We have data from stereo event cameras, stereo global shutter RGB cameras, and also LiDAR point clouds that you can see on the right. What is an event camera and why did we choose to use an event camera? So this slide is only for those people who never heard of an event camera. An event camera is a motion camera. It's a camera that measures only motion in the scene. That means if nothing moves, the output will be nothing. Here you see myself waving my arm in the field of view of the camera, and then only those pixels that measure motion basically trigger information. Now, the beauty about the event camera is that the information is triggered asynchronously, so continuously in time, in the blank time between two frames. So that means this camera has a very low latency. So how does it work? Every pixel is independent of all the other pixels, and whenever a pixel detects a change of intensity caused by motion, then the pixel will trigger an event. So it has a very low latency, no motion blur, very high dynamic range, and very low power. The problem, though, is that because the output is asynchronous, you cannot use directly traditional vision algorithms unless you do some tricks or unless you develop new algorithms that directly work on event data. So why did we choose to use event cameras for a new driving data set? And you see the problem right here. So on the right, you can see, for example, some HDR scenes recorded by a standard camera for automotive. And on the left column, you can see actually the same scenes recorded by our event camera. You can see that despite the images looking completely different, because these are actually events, however, you can see that there is more information. So we can actually see where the standard pixels were washed out. So we can, for example, see very well the exit of the tunnel, and also in low light, we can actually see more details than in the standard camera. So we believe that event cameras can actually be very relevant for autonomous driving because of their higher temporal resolution, low latency, no motion blur, and high dynamic range. So let me tell you a little bit about this new data set, DSEC data set. So here you can see our rig that actually we attached on top of a standard car. We use a suction system to attach it, and then with some cables, we were able to actually log the data simultaneously. So what type of sensors did we choose for this to record this data set? So we have a stereo event camera. We used two Prophecy Generation 3 cameras. These are basically VGA resolution cameras that have a dynamic range larger than 120 dBs. There are also Generation 4 Prophecy cameras that have 1280 pixels, but actually the amount of data is so huge that we prefer to actually start for this data set with the VGA cameras. However, we can upgrade that later. We also added the two FLIR backfly S-USB 3 standard cameras. These are global shutter cameras. The resolution you see here, 1440 times 1080 pixels at 20 Hertz. Then we also added a Velodyne POOC on the top here. And we also have an RTK GPS receiver. We also have a very large baseline, as you can see, which is 51 centimeters for the RGB cameras and 60 centimeters for the event cameras. All the hardware has been synchronized, which took actually a lot of time to do that. The data set covers a range of about 40 kilometers, but we are expanding it on a weekly basis. Here you can see all the basically trajectories that we chose. This is actually Lake Zurich in Switzerland. Here you can see a bird's eye view of the LiDAR map also recorded by our data set. And all these maps have been registered, corrected, so to eliminate any artifacts and drifts. So that took a lot of time. At the moment, we have overall 1 hour of driving data, 53 sequences, day and night, also with HDR scenes. And we cover both urban and mountains in Switzerland. So you can also see some of the Swiss Alps. We have also depth and disparity ground truth from the LiDAR. So is this the first data set using event cameras? Certainly no. There have been plenty. Here you see a list of all the ones that we are aware of. So, but actually this is the first to feature higher resolution event cameras. Okay, so we have at least 3 times higher resolution than the latest data set that was from, for example, Vijay Kumar, Kostas Danielidis. We also have accurate calibration and synchronization that was missing in other data sets. We have a larger baseline, and we also have a color stereo compared to all the other data sets. We are planning also to expand data sets to provide additional features, by the way. Now, the question is, though, how do we process the events? So here, I mean, I would have to refer you to the event camera literature. So we have a survey paper on event cameras. But what I want to show you in the next slides is some easy trick to get around all this huge amount of literature. So one of the easiest things that you could actually do with event cameras is that you could also reconstruct grayscale frames from events. And you see this in this video. Basically, we have an algorithm which is called E2VID, which we published at PAMI 2019, which is based on a neural network that takes as input events and outputs grayscale frames. These grayscale frames have all the properties of event cameras. So they come with the very low, with very high temporal resolution, low latency, very high dynamic range, and no motion blur. And here I want to show you some of the results if you run this simple algorithm on top of our DSEC dataset. So let's start from the left. On the left, you see aggregated events. In the middle, you see the reconstructed image using our E2V algorithm. And on the right, a comparison with a standard RGB camera. You can see that the reconstructions basically are HDR. Here, it's a night sequence. Again, on the left, we have our reconstruction from events using E2V, and on the right, you see a standard image at night. So you can see more details at night than using a standard camera. The code is also available, completely open source, as well as the training models, the code for training as well. What about latency and temporal resolution? Here you see another sequence from another dataset where we wanted to show you that event cameras can benefit from their higher temporal resolution compared to standard cameras. For example, on the left side, you see a slow-mo video recorded with the Huawei phone, and on the right, you see our reconstruction from events using E2V rendered at over 5,000 FPS. This is another downstream application. Again, you can feed the events to our E2V image reconstruction, and then you can use the image reconstruction as input to state-of-the-art downstream applications, for example, monocular depth estimation, like, for example, mega depth. You see that the results are actually quite accurate. And there are now a lot of papers that are actually working on actually inferring the depth directly from events without passing through image reconstruction. And here is another one where basically our reconstructed images are fed to YOLO version 3, and it shows that it still works. Again, you inherit all the advantages of event cameras because these images are reconstructed from event cameras. So no motion blur, very high dynamic range, and a very high temporal resolution. So what do we want to say with this? Basically, we want to say that there is already now enough algorithms to be able to process the events. What I show you today is that some easy to use algorithms that will allow you to reconstruct frames from events and then apply standard computer vision algorithms that work on standard frames. At the moment, what we have investigated is that you can achieve the highest performance if you go through this intermediate frame reconstruction. However, the current state of the art of event cameras is focusing on going end-to-end from raw events to the output of the vision algorithm. For example, object labels, semantic maps, optical flow, depth prediction, and so on. However, this is currently the hardest challenge, how to make these end-to-end algorithms outperform the ones that pass through intermediate reconstruction. By the way, regarding the DSEC dataset that I was talking about, we also are organizing a competition, a CVPR. It's in the event camera workshop that we are also organizing. And we have a deadline set for June 11th for you to participate. It's about stereo depth estimation using frames and events. Okay, and so there you will actually be tested against ground truth that has been hidden, and then the results will be published on a leaderboard publicly. There is also, by the way, automatic code evaluation running on our website. And then we will invite the winner of this competition to give a keynote in our workshop. Now what I want to focus the remaining minutes of this presentation is on other interesting things that we are working on. And I would like to show you another interesting application of event cameras, especially for robust perception for example, low latency and high temporal resolution applications, which is video interpolation. So event cameras, in my opinion, will never replace standard cameras because they are high-pass filters. So they do not record the still images, but only the moving component of the scene, so the varying component of the visual signal. So if you want to take fully advantage of computer vision, you should actually use both standard cameras and event cameras. Now we have work that we are going to present at CVPR on video interpolation, which is, can we actually render arbitrarily frames in the blind time between two frames using both information from the last frame as well as events up to this time. And so we call this video interpolation from events and frames. And you see this in this video. So on the left, you see low frame rate video input from a very good standard camera, 4K resolution standard camera. In the middle, you see events from a Prophecy Generation 3 event camera, so very good resolution. And on the right, you see our rendered high frame rate video. This is all made possible, by the way, by a network. Sorry, there is a technical problem. My image disappeared, so I'm gonna reshare it again. Sorry about that. Okay. Okay. Okay, I'm now replaying the slide. So this is what I was showing you. Now I want to show you some interesting results. First, the balloon sequence. So the video that you see on the right was reconstructing using frames and events. We are rendering the video at 8,000 frames per second. This video is upsampled from a standard frame-based video at 160 FPS. So, upsampling factor of 50. On the left, instead, you see a standard Huawei phone, by the way, it's the P40 Pro phone, which is the best at the moment, that upsamples the same sequence using their own algorithms from 2000 to 8000 FPS. So a factor of upsampling of 4. So not only does this video show the quality that you can get from event cameras in terms of temporal resolution, but also what I wanted to tell you is that you can actually record much longer sequences. So at the moment with the high-speed cameras, you can only record a few seconds, while with an event camera, you can actually record several minutes, okay, in the same SD card. And that's actually another additional value of event cameras. So you can record much longer phenomena because they occupy much less storage. How does this compare with state-of-the-art video interpolation techniques using standard frames? So on the left, you see our approach that uses frames and events. By the way, we call this approach time lens. And on the right, you see the state-of-the-art video frame interpolation algorithm called DANE from CVPR 18, which suffers from temporal aliasing. Here is another example of temporal aliasing that time length does not suffer from. So you can see that, for example, some of the checkers on the right-hand side get confused, okay, because of the low frame rate of the standard camera. So I hope with these videos, I convince you of the power of event cameras and also of the added resolution that event cameras have achieved in the past 2 years, in fact. Then a few words about drones. So we continue to work on event cameras for drones, by the way. At the moment, we are focusing on drone racing, so very agile flight. A few years ago, we have released a dataset called the UZH FPV drone racing dataset, which features a stereo camera, an event camera, a ground truth from a LiDAR total station. And I wanted to tell you that this dataset is available. We have a leaderboard, and it's meant for benchmarking visual odometry and visual SLAM algorithms using both event cameras and standard cameras. This dataset was invented because there is a shortage of datasets in both computer vision and robotics that tackle high-speed motion. And so we hope that actually we can get the community to work on more advanced algorithms for very high-speed motion. We are actually now upgrading this data set with a new large motion capture system, and where we'll be able to collect even more data. And this should be available by September, by ICRA. We also continue to work on dodging dynamic objects with event cameras. Now we are working also in forest navigation. We have a science robotics paper that is conditionally accepted, and if accepted, the results will be shown soon, within the next few weeks. But basically, we are using event cameras to avoid objects, for example, thrown at the drone, as well as stationary objects. This is actually a work that was published in Science Robotics last year, where we showed that using an event camera, you can actually have a perception latency of only 3.5 milliseconds. So very, very short compared to standard cameras where instead you would need to collect at least 2 frames. And so they would require at least 20 or even 30 milliseconds of latency. So with this, I conclude my talk. And well, these works were all done by my great PhD students. If you're interested in code, publications, and videos, you can find them on our webpage, and also you can follow us. Thank you for your attention.
Thank you, Davide. Before we go to the next speaker, let me just highlight what I mentioned before at the Q&A, that if there is any question to the speakers as we move forward, please message us on the Q&A, and then the speakers will be able to select some of those and respond to them in the panel discussion.
Okay. Thank you very much, Costa. So then it's my turn to invite CJ Taylor to share his screen. Thank you very much. So CJ is a professor at UPenn, and he's going to talk to us about UP Slam, Union of Panorama Slam. So I guess this is wordplay with UPenn, CJ?
I think you're cleverer than I. Actually, we didn't think of it that way. But I'm going to claim it.
Great. Then please take it away.
Okay, well, good morning, good afternoon, good evening, everybody. So I guess I wanted to start by thanking the organizers for all their hard work in putting together this workshop. It's a a fantastic lineup, and I'm really pleased to be a part of this. So what I thought I'd do actually today is to address the theme of the workshop. I wanted to talk a little bit about 2 pieces of recent work from our lab on LiDAR-based mapping, namely UpSlam, and some work on semantic cross-view localization. So both of these are actually being presented in more detail later in this conference. So I'd encourage you to check out these presentations if any of this interests you. The students will be doing it, and of course doing a much better job than I can. So first, I wanted to talk about some work we've been doing on real-time LiDAR-based mapping. This is done with my colleague Anthony Cowley. We call our system UpSlam, which stands for Union of Panoramas, Simultaneous Localization and Mapping. So let me just begin by a motivating video. So as you know, one common and extremely successful approach to handling LiDAR-based mapping is to pre-process the incoming scan to extract a relatively small subset of 3D features, which are then used to solve for robot motion. So this is an approach we've tried with some existing open source SLAM systems on a range of data sets that we collected from a number of our robotic platforms. So as you can see here, we work with wheeled vehicles, with aerial vehicles, with legged vehicles, with human carried, sort of the full range. And one thing we noticed as we applied a couple of these is that they would work well on some of the data sets, but not all. And we hypothesized that this was in part due to the range of motion patterns that we were seeing, and the feature selection process, which in some sense forced some of these implementations to make important decisions sort of fairly early in the process. So this motivated us to develop schemes that would use all the data in a LiDAR scan in real time. So that's what I wanted to talk to you about. So our approach, UpSlam, is sort of based on a few basic design decisions. So firstly, we are representing the scene as a collection of local maps arranged in an atlas and connected by a Postgraph. Secondly, each of these local maps is represented as a panoramic depth image, which is exactly what it sounds like. A local map, which is essentially organized as a 2D array encoding the structure of the scene from a single viewpoint. So in a graphics context, this would be referred to as a depth buffer. So here we see a rendering of what one such view, showing both the range and normal information in the scene. So note that these representations are sort of fundamentally 2D, which means that they're basically images, which means that they can be compressed like 2D images. And this is one aspect that allows us to sort of represent actually very large areas of space very compactly with really what ends up being a collection of images. Now, we're of course building on a lot of related work. So this is an atlas-based approach. So atlas-based approaches and postgraphs have been extensively studied in the literature. Panoramic depth maps have been proposed by our group and by others, so making a citation there. And of course, we're building on the seminal work on loam and related techniques. So this is something that definitely inspired us. So again, this is just showing an example of our system in action, just to ground us. So as you can see here, this is a system moving around, building a kind of canonical postgraph-based representation, where each of these purple boxes or green boxes you should think of as containing a panoramic map. The system is capable of doing loop closure, which allows us to do the usual drift reduction when these kinds of things are located. So what are some advantages of our approach? So first off, we end up computing a very compact representation of space, which allows us to represent large areas very efficient while preserving detail. Secondly, our panoramic depth maps are simple, regular 2D arrays, which allows us to develop highly parallel scan matching schemes, which can be implemented efficiently even on modest GPUs. So let me just explain that, or give a thumbnail sketch of how that all works. So the core computation of our mapping procedures is, of course, the venerable iterative closest points algorithm. And the entire process is laid out here in pseudocode. So the heart of the procedure, it really involves finding correspondences or matches between our current LiDAR scan and our current map. And then using these correspondences to compute an error function, which we're going to iteratively minimize using a second order method. So this figure shows how that procedure is going to play out in our implementation. In this figure, a position and normal associated with a point and scan are denoted by P1 and N1, and its corresponding map is denoted by P2, N2. And in this case, we're using a point-to-plane error metric to align these two scans. So obviously, the goal in this case is to recover a rigid transformation G that does the best job of sort of aligning these. Now, here we're noting that basically the design choices that we've made allow us to effectively parallelize this process on a GPU. So we accomplished this first phase by finding correspondences using a projective variant of iterative closest points. And on each iteration, we essentially project each of the LiDAR scans into the current local map using the current estimate for the relative posts. And this simply involves indexing into a 2D array, which is very easily accomplished. Once the correspondence has been found, we can compute its contribution to the error term along with the gradient and the Hessian of the matching objective, and then accumulate all of those in a sweep that basically sums them over all of the available correspondences. So crucially, all of this stuff can be done in parallel, which is what allows us to sort of make it go quickly. And note that during the ICP procedure, the local map is essentially viewed as a read-only array until a subsequent update step. So on this slide, we're highlighting in yellow sort of the phases of the ICP algorithm that we can actually carry out in parallel on the GPU. So here we're sort of showing how that actually plays out. So this is a implementation on an NVIDIA Jetson AGX Xavier, which is an embedded GPU. This slide sort of shows the distribution of times required to process a single LiDAR sweep. And we experimented actually with two variants of our panoramic system. One, a high resolution version, which was 2048 by 256 pixels, and a low resolution version, which was 1024 by 128. Note that the resolution of the vertical field of view is actually larger than the resolution of any individual LiDAR scan. So effectively what we're doing is super resolution in this mapping procedure. We also experimented with different power settings, namely there's a 30 watt setting and a 15 watt setting. And you can basically dial it down on this particular GPU. So here, what we're showing is the time actually taken. So with the highest resolution setting and maximum power, the median processing time is 6 milliseconds per scan. With the lower resolution panoramas, this drops to 5 milliseconds. In the 30 watt mode, it's 30 milliseconds median processing time. And for the 15 watt mode, it's 20 milliseconds. And note that in our system, new LiDAR scans are arriving every 100 milliseconds. So this performance is sort of well within real time. And this is, of course, useful to us because, again, we're thinking in terms of systems that we can field, and we want to, of course, minimize size, weight, and power on a variety of our platforms. For those of you interested in how this might work on a desktop class GPU, this is one kind of experiment where we actually achieved a 4 millisecond per scan median processing time on an RX 580 desktop class GPU. So there are, of course, more to UpSlam than I'm sort of sketching here. So this slide is kind of showing a block diagram. So we're applying inertial compensation to the IMU, to the LiDAR measurements using data from the IMU. We're computing surface normals based on the range data. And then this information is passed to the iterative closest point procedure, just as we described, to recover the displacement. When the overlap between the current LiDAR scan and the current local map falls below a certain level, or the LiDAR has moved a certain distance, then we add a new node to our graph, and that becomes part of our postgraph. And there's a separate process that I'm not describing to detect loop closures and to optimize the overall postgraph structure. Okay, so this movie just shows one example of a model we recovered from data we obtained with wheeled robots driven around the home of one of our collaborators. Hopefully this is playing. And I guess what I just wanted you to note is that the point cloud that we're displaying here is really just simply the result of concatenating point clouds associated with a few dozen local panoramic maps. So nonetheless, even though this representation is pretty compact, we're still able to capture relevant details like the structure of the fence or the washing on the line, even though this is actually a relatively small amount of data. So we've also carried out experiments to evaluate accuracy. I'm just sort of showing one here in the interest of time. So this is results obtained on a data set acquired by researchers from Oxford. Plot on the left overlays ground truth with the recovered trajectory. Two trajectories are pretty close, except at the very distal ends with a median error, in this case of 0.62 meters over a trajectory of around 1.4 kilometers. So hopefully this video will play without incident. So this video is also demonstrating some novel volumetric rendering techniques that Anthony developed, allows to visualize the collection of panoramic images at interactive rates. So this is all done in real time, and also incorporates sort of various lighting effects and the like. So here, what we're doing is using panoramic depths to sort of infer volumetric structure for the scene, and that's what's allowing us to do a couple of these effects. This portion of the video shows the results obtained driving around Morgantown, Pennsylvania. And again, here we're visualizing the compressed representations that we're constructing of the entire scene. Okay, so again, just to give you an idea of this slide sort of summarizes the data capture of Morgantown. The entire representation consists of 1,045 keyframes. Took approximately 1.2 gigabytes on disk, which is a substantive distillation from the 20 gigabytes of raw data. And we believe that actually more compression is possible by applying more aggressive algorithms to our data. So to summarize, in Upslime, we are adapting this atlas-based approach to LiDAR-based scene mapping, where each of the local maps is represented using a panoramic depth map. And the fact that our local representation is relatively simple allows us to use GPUs to effectively accelerate the ICP process, which is used to estimate the motion of the platform. And this in turn allows us to exploit all the available LiDAR data in real time and increase robustness that way, even on embedded computational platforms. So I wanted to switch gears a little bit and talk about some related work that's built on Upslam. And this is a system that we've developed for using information from aerial vehicles to help localize ground-based vehicles. And we refer to this problem as cross-view localization. And this is work that's been spearheaded by my colleague, Ian Miller, who's shown here. So the problem that we're actually interested in here is how to endow our ground-based robots with the capabilities we would have as tourists. So if we visit a new location for the first time, and we're interested in figuring out where we are with respect to an overhead map, we might do something like observe that we're near a park, next to a river, across the street from a large building, and use that context to identify where we might be on a map. So in our algorithm, what we do is we're making use of the semantic labeling network to extract information from the aerial and the terrestrial imagery, and then fuse that information with our geometric context in a particle-based filter localization scheme. So here what we're doing is simply showing one approach to augmenting our panoramic imagery with semantic imagery. In this case, this is done by applying a semantic network to images gathered by our mobile robot and projecting the results into depth panorama. Nowadays, we actually do this by directly processing the LiDAR channel, so that simplifies matters a bit. So we also apply semantic analysis to our overhead images. So this is semantic analysis applied to kitty imagery. And in this case, we're simply using 4 main classes: road, terrain, vegetation, and building, and using a pretty standard network for doing this. So additional classes are sort of readily added if needed. So a thumbnail sketch of the approach is actually pretty simple. So from the overhead image, we can predict to a certain extent the geometric layout and associated semantic categories that we would expect to observe from various vantage points in the scene. And we are, in this case, representing these expected views in terms of 2D polar maps. We can then compare these to the polar representations derived from the panoramic maps, which we built from the ground-based platforms. Our entire process is then just incorporated into a particle filter-based scheme, which allows us to track the position of the ground robot over time. So let me give you an idea of how that works. So again, this is being applied to a small town in Pennsylvania. And again, the system starts off with no idea where it is initially. And then by fusing both these geometric and semantic cues, it's actually able to localize itself with respect to the 2D overhead image. And that, of course, provides us with additional context. Okay, so this next section is showing this applied to actually the city of Philadelphia, so our neighborhood. And once again, even though this is actually a fairly regular scene in terms of a regular north, south, east, west grid, it turns out in this case that trees are actually relatively sparse in Philadelphia, and that actually turns out to be a useful cue when combining these LiDAR, the semantic analysis. Finally, these are results on Kitty. Again, a very different kind of data set, but again, same procedure, works quite well. System is able to localize effectively. And of course, once we have localization results from this, we can actually imagine fusing these back into our pose graph, which is something that we do, which again is a way to help us counteract drift or other issues. And lastly, of course, once we've done this, we can actually fuse our 3D analysis into our 2D map. One thing we found this very useful for is actually for correcting errors in the 2D overhead map, which can be outdated, might not have certain features that have changed over time. We can actually correct for that by using our ground-based information from our ground-based platform. We've actually done results to sort of characterize accuracy on this, which I'm not going to go through in great detail. In this case, it's we inherit some of the useful properties of the particle filter, and that we're able to actually recover effectively from momentary losses in localization, and again, by exploiting both the geometric and the semantic cues, which help us to do that quite effectively. So to summarize this section, our panoramic representation can be readily augmented with a semantic layer, and the semantic content provides a mechanism to match terrestrial and aerial views to achieve the kind of localization results that we want. So to conclude, what I've tried to do in this talk is to briefly describe two ideas that we've applied to improve robustness. The first idea is to use parallelism to process all the available LiDAR data and thereby give us sort of multiple bites at the apple in terms of being able to match features. The second idea is to incorporate semantic content to provide a richer context for localization. And in our experience, this has actually helped to improve the robustness of the system by basically giving a new set of criteria that can be used to solve these kinds of problems. So with that, I will turn the floor over to Sebastian.
Great. Thank you very much, CJ. So I noticed this up slam, which sounds much better than UP slam. Thank you very much for this talk. Yes, so Costa.
Yes, so next speaker is Sebastian Scherer, Associate Research Professor at Carnegie Mellon University. And Sebastian will give us a talk about robust navigation with visual and thermal sensor integrated visual environments. Sebastian will give this talk in a pre-recorded manner, and later afterwards we'll have the panel discussion. So I'll start the video now.
Hi everybody, my name is Sebastian Scherer. I'm an associate research professor at Carnegie Mellon University, and I'd like to talk to you about some ideas that we've been exploring to move towards robust SLAM. Also, if you get a chance, please check out our Tartan SLAM series of talks that focus on various ideas around SLAM that is just kicked off last week. SLAM is a key function of robot systems. However, right now there has been a lot of focus on SLAM in nominal situations and accuracy. However, what we are interested in is how can we still get a good pose estimate even if there's a lot of degradation in the environment. And for us, robustness is often more important than accuracy. So I'd like to talk to you about some ideas that we've been exploring on how we try to make state estimation more robust. First, I'd like to talk to you about superodometry. SLAM systems are very vulnerable to a single modality causing issues and a dropout in performance. And ideally, a SLAM system should be fail-safe and failure-aware. Additionally, we want to avoid problems with incorrect data association, as well as potential sensor dropouts, and be aware of how much computational resources we have available. Superodometry foremost focuses around the IMU to create a state estimate. So the IMU is integrated to give a position and velocity, and drift rates are corrected with other sensors, which might or might not work. And the hope is that hopefully a combination of the sensors will have uncorrelated dropouts. While previously IMUs are often disregarded as being very noisy, they actually are very good sensors to give a state estimate as long as we can accurately constrain the bias. And that's the key idea behind superodometry. So rather than trying to build a big factor graph that takes everything into account, it would, which would be very fragile for outliers, instead the approach we take is to create an IMU odometry and then try to constrain the drift of the IMU odometry with various other odometries. And each of these is a factor graph in itself. And so then we have a set of little factor graphs that we solve. Another advantage is that this allows us to do selective fusion, where, for example, in a situation where there's no thermal contrast, then we would not use the thermal camera. Similarly, for visual or LiDAR data. So let's look at some examples. So if we just have visual and LiDAR available, then we would do laser data. If we don't have good camera data, we might have laser IMU and other sensors such as thermal cameras. Or on the other hand, if we are in a situation that has no features for the geometry, we would now rely more on the cameras. So let me show you some examples of how this looks like. So here's a narrow hallway with not a lot of geometric features, so it's kind of bad for laser odometry. However, there's good visual features, so visual odometry works. And the key that we're really trying to show here is that the method is automatically able to choose which modality works well without us having to tell it to do that. Now, in addition, the laser still gives us some constraints that can get fused in the method, so this leads us to very high accuracy, even in this kind of degraded situation and suboptimal motion. Now, here's an example where the camera data drops out. So we go into a dark room, we lose features, and then we come back out and we have some aggressive motion to try and make the state estimation more difficult, and see that in this situation the laser is able to overcome this, and our third or selective distribution allows us to still have a good state estimate. You still see that the map is still sharp, even though we had this camera drop out and coming back in, where both the laser and the camera drop out. So there are several sections of very high dust where typical laser odometry, as you can see in the bottom and the right and top, will just fail. But since we in these situations rely more on the IMU, we can still successfully estimate the motion. Here you can see us purposefully doing aggressive motion, and you can also see that the image quality is quite bad. The image is dark, and you can see how well the state estimate works after we encounter this dust cloud. So you can see here in these challenging situations, compared to a lot of the single sensor methods, our method is more. We've tested this on various platforms and with various sensor computers. So some of the highlights of the method are that it's extendable to different sensor modalities. So here we have vision, LiDAR, and thermal, but you could imagine other modalities could be added. And it's quite a simple approach. And since it solves these decoupled problems, can also be faster to implement, and really kind of rests on that key insight that IMUs can give you good odometry as long as we can constrain the drift. Here are a couple of maps from previous experiments with super odometry. Now next, I'd like to go in a little more in depth on the thermal odometry part of it, since it's more unique than the. So for some parts of the challenge, there is fog in the environment, and you'd still like to be able to navigate in fog. If fog is really bad, then neither visual nor LiDAR data can provide you useful constraints. So range data will just be occluded and visual images will be occluded. Thermal images are not affected by this type of fog. However, you need sufficient thermal content. Now, a thermal camera is not exactly like a visual camera, and it has some challenges that make it difficult to use it effectively. One of those is that it has some fixed pattern noise, it's low contrast, and sometimes there's very little signal to noise ratio, and the cameras have built-in shutters that cause data interruptions, which makes it difficult to track visual features and extract them effectively, which is what a lot of downstream methods rely on. Another challenge for us is that we want to use this on a mobile robot, ideally a flying robot with limited. Now, there are a couple of ways to try and get features from an image. The classical feature extractors are Harris features, good features to track or observe many features. However, these features often can't handle the image transforms the image goes through as in time, and cannot handle the lack of sharpness in the images. On the other hand, there are many learning-based feature extractors. However, these are typically designed for visual features. There are several thermal odometry methods, but these methods rely a lot on high-quality thermal images, which are hard to achieve. So our work splits into kind of 4 parts. So one is to try and learn a robust feature extractor for thermal images. Then a feature tracking method, and then a bundle adjustment approach that is robust to outages of the thermal images. First, let's talk about the training process. So the 2 ideas that we apply here is to try and reduce the noise and try and apply pseudo feature supervision to try and robustly detect features. Next, we have developed a new network called the thermal point network that has a shared encoder which abstracts high-level features and reduces the dimensionality from the input image. After that, the architecture is divided into 2 decoders. One is a feature detection decoder and the other one is a descriptor decoder. To improve real-time performance, we don't use the descriptor decoder and only use it during training. And the idea is really to try and optimize this to give us robust features in these thermal images. Now, once we can extract this feature, how do we use these features in an odometry approach? So to track these thermal features, we use a radiometric feature tracking approach to establish feature correspondences across images. And another reason for that is that it's often possible in thermal images to sample them very frequently. So 60 Hertz images, for example, are not a big problem. So this radiometric feature tracking can be quite effective. We also integrate the IMU, as we discussed before, to then cover any of the outages and also improve the feature tracking. And then we take this data and merge it together in a thermal inertial bundle adjustment to estimate calculated pulse. Details you can also look at our paper. So here's some comparison between SIFT and thermal points for feature tracking, and you can see also some of the difficulty in these thermal images. And so you can see that in thermal point you get a nice kind of spread and good matches between features, while for SIFT you see many wrong matches and often few matches. You can also see a comparison on how well the detector can handle this fixed pattern noise that often appears in thermal images. And you can see that in that strip of noise, thermal point extracts fewer features. On the left, you can see the accuracy of odometry in an indoor situation, and thermal point odometry is shown in blue. And you can see that our odometry is closest to the ground truth. You can see also a comparison with various off-the-shelf. Here's a comparison between LiDAR odometry and thermal odometry in the situation of heavy fog, just to kind of illustrate that even with a good LiDAR in a relatively small environment, if you have enough fog, then you will not be able to penetrated also with the LiDAR. So here visually, we're not able to see enough, and you can see now that the LiDAR odometry started to drift. However, the thermal odometry is still able to run quite well on this and has a small drift rate. Just to summarize, so we presented a tightly coupled deep thermal inertial odometry algorithm, new feature detection network, and some IMU-aided radiometric feature tracking method. And we evaluated robustness in various situations. And so one of the key insights in our approach is to try and use radiometric data and treat it not like an image, but try to use it in closer to the way it was collected. So using full 16-bit images, and then also trying to leverage this higher frequency of data. And again, combining the IMU with the thermal data allows you to get more robustness both in the tracking as well as the estimation. Now, even if you can calculate your position in degraded situations, often now you have to know what to do. And so here's just some initial approach on how we quickly try to filter dust before we do any type of probabilistic mapping. So one of the indicators of dust is that you have sudden steps in the distance and very spurious steps in that distance. So we look at these kinds of steps that are surprising and then use them to calculate which points are good. Additionally, what distance step is used, what the threshold is, essentially is distance dependent because you have more point separation at longer distances. And here's a comparison of what that means in a longer hallway. And so in red, you see points that would get filtered based on dust based on distance steps, and green would be accepted by range in the x-axis. So as you get further away, you can have bigger steps and not treat points as dust points. And so we can use this information to then, in real time, filter points very quickly before we even have to worry about probabilistic filtering of these points, which then can reduce the effect of dust points even more. To summarize, robustness is often more important than accuracy for autonomous systems, and we developed a framework that can accommodate multiple modalities robustly and demonstrated results showing those for various combinations of visual and LiDAR fusion. Additionally, thermal cameras can be another modality that can increase robustness. And then filtering on the mapping side can also enable you to navigate in these dusty situations. Now, one of the questions maybe for the discussion would be, how do we define robustness more rigidly, and how can we move from focus on accuracy in benign situations to a good metric for robust estimation? Thank you.
Right. So thank you, Sebastian. And I think we have Sebastian with us now.
Yes.
So, hi. So with that, I think this was the last speaker talk of the session. And we now enter the panel discussion phase for today, for this session. And first of all, to all the participants in the meeting, please use the Q&A in case you want to ask a question. Otherwise, you can raise your hand, but the easiest way is to use the Q&A. And just to get the discussion going, I will start directly with a question to you, Sebastian. Give us some opinion on the following. So for the super odometry paper, I think for you also one of the major goals is to ensure maximum resilience of the localization process, especially in these challenging integrated environments. And you also mentioned in the presentation that essentially the method auto detects which modality has better ability to constrain the solution. And first, I would like you to ask if you can provide a bit more detail about how this happens, as it's already in the paper. And then second, I think there is generally two ways of thinking, more like tight fusion, where people will try to integrate visual landmarks and also features from LiDAR and so on and so forth in one single optimization step. And this might have some computational cost, but also potentially some benefits. So I would also like to ask your thoughts about this, let's say, difference in perspective between loosely coupled approach and more tight fusion.
So I guess, so on the first one for the detection, so for the LiDAR part, what we're essentially looking at is the constraints. So it's essentially for the LiDAR odometry part, it has different extracts features, basically match those, and then depending on the distribution of your normals, for example, for plane features and so on, you know which axes are constraints, and so that's in some sense a very similar idea to the way LOM does the constraining. And then for the visual part, you're looking at kind of a couple different ideas, and I think that's I think that that's something that's still kind of actively in work. I mean, we have one way to do it now, which is again looking at, for example, like an SVD of the covariance, seeing how many axes are constrained, saying, oh, this is good. But I mean, that really only tells you, that can still trick you because it only tells you relative how unconstrained is relative, not how much, how good the overall solution is. So yeah, so there's still a couple of other ideas we're looking at, and I think that's still in progress, I'd say. And it's especially for the visual part, it's not as clear, like when it fails and when it doesn't fail. And then in terms of loosely versus tightly coupled, I guess this method's kind of somewhere in between. So I mean, it is essentially loosely coupled, right? So you have a bunch of different odometries. Each of the odometries are tightly coupled in a sense. I mean, that's that they solve a little factor graph problem, but then the overall integration is loosely coupled. And I mean, in theory, tightly coupled should be better. I guess in practice, the problem is that once you make a mistake, then your whole optimization problem starts becoming a little unstable. And then if you want to be robust and have some kind of multi-hypothesis or multimodal kind of solution, then the optimization becomes really slow. So that's so until we can kind of figure out, and maybe computation gets all better, we kind of being stuck with loosely coupled, and at the cost of potentially some accuracy. I think it's
right. I think this is a big problem, because in principle we can have a more accurate solution, but it's very difficult to make it robust afterwards.
Right, and it's I mean, I almost think about it, like similar to, I don't know, PID loops and MPC, right? Like, PID is very robust. MPC probably has higher performance if you can have a good model, but then if your model is bad, then the whole thing kind of just blows up. And
I'm personally hurt at the moment. But I guess we can go on. Thank you, Sebastian. So I guess we can go to other questions, maybe just to go for a first round. And just to mention, I forgot to mention from my side in the beginning, Davide will join slightly delayed. So questions to Davide maybe can be posted already, but we will Davide will have the opportunity to address them later.
Maybe in the meantime, I ask a few questions. So Sebastian, I think you posed a great question in the end, but I'll keep it to pose it to you, to hopefully to all three of you, if Davide manages to join at the end. But in the meantime, maybe CJ, I'll take off where Sebastian and Kostas left it, where we said if there are mistakes, then what happens in the optimization is a different problem. But so what happens in UpSlam when there is a misalignment, problem in data association? If there's a mistake, basically, is there any way of undoing it?
It's an excellent question. I mean, so there are actually a number of aspects to it. And again, I would encourage people who are interested to talk to Anthony, who will be talking later. So actually, in the current system, basically all of our maps are stored in the system. So there's effectively a database, and there's actually a procedure that's actually going back through the database and looking at possible hypotheses in effectively the computational window that we have. So actually, that's one of the things that we like about this system, is that the representations are compact enough that you can actually go back and do a little bit of hypothesis testing if you think that you're missing stuff. I don't think that's a complete solution, honestly. And actually, I think that some of the things that we're trying to think about now in terms of incorporating semantic analysis, we hope will actually get us further down that road in terms of being able to recognize when you're seriously off, or at least be able to characterize appropriately distinctive locations. So that's a kind of a thought that's in the back of our mind. So yes, there is actually a process in UpSlam that's actually trying to do that. But I wouldn't claim that that's a complete solution to the problem. I think there's still much more to be done along this line.
Okay, and I mean, you showed some. And I think it was it was still the first part of your work. So you mentioned that the system runs, so you take a scan every 100 milliseconds. And then you showed some results with a car, maybe it's a second part with a car running at 50 kilometers per hour. And I was wondering if that rate is enough for good accuracy.
Yeah, it is. I think that there's, honestly, I think that there's a little bit more we can do there. So I think that there's aspects of the motion model which I think are actually not quite correct for those high-speed things. It was kind of good enough for what we were doing there, and we wanted to just sort of push the thing around in various speeds, various kinds of motion modalities. So we were pretty pleased that it's the same thing. I think there's like a 1-parameter change in terms of maximum allowed velocity between all of the experiments that we ran.
Right.
So yeah, we were pretty happy with that, but definitely, I think I think it's one thing. It's a discussion I'm continuously having with Anthony, as I think that there's different formulations of the motion model, because pretending that it's 100 millisecond stand is actually not correct. They're better.
Okay. Costa, I think there's a question from the audience.
Yes, and it relates, so maybe it's a good time. So the question is the following: if the loosely coupled approach is promising in visually degraded environments, does the exact hardware time synchronization of sensors is required? Can we tolerate timing differences up to a few milliseconds, let's say? So maybe you, Sebastian, or CJ, want to comment about this?
I mean, we try to solve the time sync problem regardless, just to make our life easy. You don't want to turn that into a research problem. I mean, it all depends on your motion, like how aggressive, how fast, if it makes a difference. I think like if you have, like, for example, very high turn rates, then you have to get your sync down, even if you're doing it loosely coupled. And then especially for something like super odometry, still solving a factor graph problem between the IMU and all the odometries. So if it's off, then then you're going to misestimate the biases in the IMU, and then you're going to be off worse.
Mm-hmm.
Yeah, so from my side, I also want to iterate on the same, I would like to say. So I think problems that we can solve a priori, they're better to be solved a priori without turning them into a big challenge. So yes. As we wait for other questions from the audience, I would like to ask you, CJ, one question for your work. And it's it will relate a lot to our interests. So you demonstrate that you have significant compression. And in certain instances in your video, I saw, for example, the traffic light, which is, let's say, a thinner feature, but it was preserved. And I would like to ask, is there any particular aspect of the work about how to selectively preserve thin 3D features while overall we achieve compression? And overall, is this something that you're doing more research at the moment?
An excellent question. Actually, in part, some of our initial thinking about this kind of representations came out of thinking about humanoid robots, where we were interested in grasping, and we were interested in being able to resolve, let's say, pens on a paper while still being able to map large areas. And really what we're relying on is, in some sense, the fact that projective representations sort of have that as a natural property, in that you get this natural distance-based resolution, which you can either view as a problem or try to exploit as a useful property. So really, because we're sort of representing with these individual projective representations, you get the natural property that when you're close to things, you get high resolution, and that's sort of preserved by nature. And stuff that you really didn't ever get close to, that's the resolution that you have it naturally in your representation. So the short answer to your question is, actually, we don't do anything special per se, other than just using just taking these projective representations and just using them in the way that they're coming to the system.
Got it. And there is a follow-up question for you, so I will read it. It says, CJ, you briefly mentioned super resolution of the LiDAR image. Can you provide details on how that is computed? If it is just interpolation, does it add new information?
Excellent question. So effectively what happens is that the local representation that we're constructing, let's say it's 2048 by 256, and let's say an individual scan might be 1024 by 64. That's what's coming out of the LiDAR. Really what's happening is that because that local map is being accumulated over, let's say, a 5-10 second window, whenever we do a registration back to the local map, that effectively helps us to fill in missing points. So you get this kind of super resolution effectively, naturally, just because you're integrating multiple scans over the course of a system. So we avoid interpolation, in some sense, trying to make up new data where it isn't. So if there's a particular section of cell in our map that doesn't have a circle on it, effectively, we're not worrying about it overly, because we have enough data that there to do relative matches.
Great, thank you.
Maybe I have one for Sebastian. So Sebastian, you showed, and you mentioned very nicely in the talk about how the system is able to identify which modality works best and choose, instead of, the designer to choose which modality works best. And that was between, I think, LiDAR and vision. Am I right?
Mm-hmm, mm-hmm. Yes.
And then you went on to show results with thermal inertial. And I was thinking, it's a brilliant idea to teach a system by itself to understand what it should rely upon. And is this where we're going to try and have more and more sensors, and then just try to teach a system what to select, which sensor works best?
Right. I mean, I think so. The only other thing I want to mention is, so it's not just turning a sensor on and off. It's actually choosing certain degrees of freedom to integrate. So for example, it might be that in a hallway, left and right is very constrained with the LiDAR, but forward you don't have a lot of information because there aren't any features. So it kind of picks which dimensions. And I mean, I think for these degraded situations, you need you need to be able to overcome these different situations. So, thermal is nice, but I wouldn't want to just it depends on kind of problem. But if I wanted really high accuracy, in addition to robustness, then probably thermal alone is not enough, because it's going to drift more than the other modalities, just because it's fuzzier image and so on. But it helps you not be lost in situations where the other sensors go.
In your example, so you showed in the comparison between visual and LiDAR, you said yes, when it's very dark, then LiDAR is helping out. Do you have situations where vision is selected over LiDAR?
Right. Yeah. So I think in that I think I showed the example. It's basically for example, in long hallways or narrow rooms, the LiDAR will not give enough constraints. Or for example, shafts, if you have like let's say an elevator shaft or something like this, then the LiDAR will tell you very well where you're inside the shaft in X, Y, but in terms of Z, it doesn't really help you.
Cool. I will go back to CJ, because the question before there was a follow-up. So maybe it's just an add-on, CJ. In this panorama image, how is the panorama image different from the RGBD image, essentially?
It is, I would say, similar in that, it's again, it's nothing more than a 2D array, I guess, in the way I think about it. And I think that's sort of I would argue that sort of the simplicity of that representation is what sort of allows us to, sort of process these things very efficiently and store them very efficiently. But the union of them, which is sort of the U part, is what allows us to sort of reason effectively about the 3D structure. So for instance, we're able to do things like analyze collections of these things after to discover moving objects because of inconsistencies between different pieces. So yeah, see, really what we're saying is that we're representing a 3D scene with a collection of effectively 2D images, and it's not RGB, but we definitely see this 2D structure as a simple structure on which you can then leverage other information, be it intensity, be it semantic information, and the like, and keep the representation sort of individually simple, individually compressible.
Great. Yes, I think, Sebastian, you posed a very nice question at the end of your talk. You said a lot more words than I was able to remember, but the gist of it was, how do we quantify robust perception? I mean, please elaborate and tell us a bit more. Your question was much nicer posed than mine. But I don't know about that. Both of you to comment. Yes, please.
Yeah, but I mean, I think I guess the point that we that I think requires some discussion, right, is that in the SLAM community, or not, maybe just not in this community, but maybe outside, in the all the CVPR, more CVPR direction, the process is often take a data set, iterate on an algorithm, post best result on Kitty, UROC, and what is it, maybe TOM data set, and then keep improving. And and that kind of misses a lot of access. And I guess one that's specifically important, I think, for robotics is robustness. And so the question is, what's and it's just harder to quantify, right? And I think if you have a good metric, then people will try and beat it. It's like a computer game, right? Like so I think and I guess the reason robustness is tricky is it's not just it's sometimes it goes beyond the pure algorithm. It goes into what are all the if statements and all the things surrounding the algorithm that actually make it robust. But I mean, in terms of metrics, I think that's something that we are currently trying to improve. So we're working on this Tartan Air version 2 data set, and we'll try and have a better robustness metric in there. I mean, right now I think what we had right now is very simple, where basically the algorithm self-reports if it thinks it's valid, and kind of that valid percentage is what's, we look at robustness. But I think you could think about some maybe maximum drift rate that would be allowable for the system to still perform reasonable, and then over some time window, something similar to RP or something like this, and then look at some percentage of this maybe, and you would want maybe a high percentage. Or I mean, I think that's like an open discussion. Again, what's a good metric that represents what we need, right? I think there's some the other thing is there's, I guess, some the other thing that often gets I think neglected that's important for robotics is velocities. I think is another thing. I don't know that pretty and that's something we kind of found out ourselves when we looked at super odometry because you looked great and then the velocities are all noisy. Okay, and now you got to fix it, right? And so I think that's maybe another thing. Like, I think it would be good to have some discussion about, again, what's a good metric, and have some agreement on this.
CJ, please.
No, I just wanted to comment, because I think, Sebastian has put his finger on, of course, a really important point here, is that, and I think there are two aspects that I've raised. I think one is in terms of the diversity of situations that are encountered within a data set. And actually, I think Tartner does a really nice job on this in terms of exposing the system to not just kind of, Kitty is a wonderful data set, but obviously it's within a particular context, and pretty much all the data looks very similar. And being able to have data sets that actually expose you to a wide variety, and this is something we started touching on, is when we had legged motion plus aerial motion plus that's when we started to sort of push, see sort of failure modes because just they're trained in different points. The other thing, and I think this is something I've thought a little bit about in Davide as well, is accurate reporting of uncertainties. So actually, and this is actually a tricky issue as well, is that if you look at something like monocular depth prediction, where you're asking the system to predict depth, again, the easy thing to measure is accuracy. If you have something that's actually saying, okay, this is accuracy and this is uncertainty, actually evaluating uncertainty, it turns out, is actually pretty tricky. What does it mean to have a good uncertainty estimate? And do we have agreed ways of doing on this? And this is sort of close to my heart, because my student and I just went through, looked at like 6 or 7 different metrics for talking about how accurate is your uncertainty. And this is tricky. So I think that's something that's maybe worth also kind of surfacing, is having algorithms that actually try to report uncertainty and trying to be able to evaluate uncertainty as well as accuracy in some way that we can agree on.
Great. Maybe we welcome Davide back in the panel. So Davide, I will bring you up to speed. This is a question that we pose to all 3 of you, hopefully, is how to quantify robustness in perception, and what are the metrics that we should be using. And we've heard ideas such as improving the diversity in our data sets. Kitty, TUM datasets, they have their own set of challenges. What is the next best thing that we want to address? And then Sebastian also mentioned maybe the rate that we are drifting. I guess for odometry systems, this is pretty good measure. And also the velocity estimates, right, Sebastian? Did I miss something out?
Yes, actually, I guess what I was thinking is some maximum acceptable drift rate and a percentage of this, or something like this, and maybe
it's very relevant for odometry systems, because when we talk about SLAM and we think about the loop closure problem as well, then it's a whole different story. Sure. But I agree with you. I mean, if we're thinking of robotics and having onboard perception live, then odometry needs to work well as well. Right. Sure, we can correct with the loop closure, but what happens in the meantime? Yeah.
Right.
Okay.
Davide? Yes.
So I think it depends very much on the task, right? So let's try to be general. So in general, we are talking about robust perception. We must take into account the failure rate, high dynamic range, motion blur, smoke, and other things. For example, in my case, that we are working on event cameras for high-speed navigation. HDR and motion blur are the most prominent ones. We have a metric for motion blur, which is the endpoint error. So basically, we have proposed this in the FPV drone racing dataset that was published in ICRA 2019. So in that dataset, in fact, we take all the published datasets for VIO, VI SLAM, and then we computed the endpoint error of each we computed the optical flow for each dataset, the average optical flow, and then we plotted it. And we show that basically it's not very high. So if you want to go at very high speed, typically you will have a very high optical flow. And we show that our dataset actually reaches a higher optical flow. So that would be a metric for benchmarking algorithms against motion blur. For HDR, I don't have a metric. I would be happy to have one because it's difficult to quantify HDR. I mean, we can borrow some metrics, I guess, from people that are working on semantic masks. So the IOU, intersection over union. So these things can be potentially used in order to quantify what is the amount of pixels that are occluding, masking out the main signal that we want to process. But we haven't done it. But I think this could be an idea. Failure rate, instead, we know how to measure it, right? So, for example, when we fly drones, we measure the failure rate as 100% only if you complete the tasks, without ever crashing. So in drone racing, we count the number of correctly flown laps, or in drone acrobatics, we count the number of correctly flown trajectories. But you can also make it proportionally to the amount of laps that have been flown. So there are also some ways to adjust that. However, there is no agreed upon measure. And that's why it's very important that in papers, actually, we clarify very well how we measure the success rate and so on.
So for you, you call it now a success rate, right?
Mm-hmm. Yes.
Success, what would you describe as a success? As in reaching your goal?
Yeah, exactly. So what I was saying is that, for example, for autonomous drone racing, typically you want to complete the track autonomously without ever crashing until the end. So if you do it, then it's 100%. If you even crash once, then it's a failure. And you take it into account. Other people instead, they count the amount of the fraction of trajectory that has been completed. So you can use whatever you want, as long as I think the papers specify exactly what they're using, because there is no agreed upon measure across papers, unless people, we as a community, we start to standardize it. Kitty did a very good job. They defined this for SLAM, though. For SLAM, they used the relative trajectory error, the absolute trajectory error, and these are still used today. The problem is in these metrics is that everyone using them uses different parameters. So there are about 20 parameters when you use these metrics, like the amount of poses that you use for aligning the estimate with the ground truth, and they are never reported, actually very rarely reported. So we actually published a toolbox 3 years ago for that has pre-defined thresholds and parameters. So you use this toolbox and you make sure that basically everyone is using automatically the same parameters. And there is also a tutorial that reports that.
Okay, so in light of this discussion and also the fact that we have about 2 minutes left, I think it's good to maybe do a small round. And I will ask very similar things. So what is the next best thing that you think is one needs to do if you want, in your area, or maybe more generic in our area as a whole? Because of course, every one of us is looking at the problem from their own perspective and also trying to generalize. I think we can see that we have a lot of concepts of what we mean by robust perception. It could be the success rate, it could be the drift rate, right? So yeah, the question is the following: what is the next best thing to robustify perception in your area or in general? CJ?
This is not novel, but I do think that sort of semantics are going to have an interesting and an increasingly important role to play. I think that's, there's a lot of great interest and a lot of great work being done in this area. And I think that that's actually going to help us sort of going forward and having systems that understand more about their environment and therefore are able to make better decisions.
Great. semantics. So Sebastian.
So I think, for us, even just having odometry, I think is a that works good enough.
Good enough.
So all I'm happy with. That drifts not, that doesn't drift a lot, right? In all situations that you could face, I think is a big step, right? Like we're not there. I mean, vision isn't even close, and even with LiDAR, it's it's even that doesn't work very well, right? So I think that's kind of the direction we're moving in. It's just having good enough odometry.
Robotic odometry with the metrics that you mentioned, but I think
right.
This is a basis. Without odometry,
yeah.
I mean,
you can't even control your robot without odometry,
yes.
right? That's basically what it comes down to.
And
I mean, you can, but yeah.
Please. So Davide, closing remarks. The next best thing.
The next best thing is, so we are working on making drones fly better than human pilots. I think as a community, we should outperform humans. Google did it with AlphaGo, so we should have our own favorite sport, robot sport or whatever, robot task, and make it better than a human. So if you're working on manipulation, I don't know, for example, tidy up a room or fold things. If you're working on cars, drive a car better than the best human. Remember that humans are remarkably good at driving. So if you remember the presentation by Gil Pratt some years ago, he said that they make a mistake there is a fatality every 10 million driven miles. I mean, that's amazing. And we are not even close to that. So take one task that you can do very best as a human and try to make a robot that does it.
Okay. A reasonable goal.
Thank you all very much for this brilliant discussion. I'm leaving the session with a lot of good ideas. So thank you on behalf of both Kostas and myself. Chris, the word is with you.
Yeah, thank you everybody again for all of your time and the time you spent on preparing your talks. We really appreciate it. So now we're going to switch gears. We have a poster session after this. It requires our moving to a different Zoom link. I have a little share screen slide for us. It's just going to show a link and then also the URL to our agenda in case you want that. So if everyone could please go ahead and make their way to, I'm guessing you can see this link, right?
Yes.
Okay, great, thank you. So please make your way to the poster session. We have several papers that were accepted as part of the workshop that would love to give some presentations and hear your questions. And we'll be reconvening in this URL at this link in just a few hours. There's going to be a poster session, then there's a short break afterwards. So we'll be back here at 13:30 Eastern time. Thank you again. See you there.
Thank you. Bye.
Thank you.
Thank you, guys. See you soon. Bye.
Bye.
Challenging. It's a great pleasure to be here. I'm Luca Carlone, I'm assistant professor at MIT. I will be co-chairing the first part of this second session of the workshop together with Professor Chris Heckman. We'll get started directly with an amazing talk. It's a great pleasure to introduce our first speaker for this section. It's a pleasure to introduce Professor Jeanette Bogg, who is assistant professor of computer science at Stanford University, and she's going to lead here with an amazing talk called Detect, Reject, Correct, Cross-Modal Compensation of Corrupted Sensors. Here we go.
Hello, everyone, and thank you very much for inviting me to this workshop on robust perception for autonomous field robots in challenging environments. My main area of research is at the intersection of robotics and control, machine learning, and perception. And I'm specifically interested in new algorithms for robotic manipulation tasks. In this talk, I will present a new approach towards robust perception when facing corrupted sensors, and that work was done by my student Michelle Lee, her advisee Matthew Tan, and our collaborator Yuki Zhu, who's now at UT Austin. So humans have this extraordinary ability to combine our different sensory inputs to reason about the world. Here's an example of a child playing the game of Jenga, where the goal is to remove blocks and stack them on top of the tower without the tower falling over. If you have ever played this game, you know that to pick which block to remove can only be determined visually to a certain extent. This game actually requires a sense of touch to feel which block is loose. And so wouldn't it be great if a robot could also use these different complementary sensory sources? Because our robots, they do have a physical embodiment, although quite different from that of a human. And they have typically many more sensors than just a camera. A robot has touch sensors, step sensors, microphones, torque sensors, and many more. And our hypothesis is that by using multiple modalities, we can achieve higher accuracy or success rate in manipulation with less data. So the more data points you have that have multiple modalities, the less data you need to reach certain levels of accuracy in perception or to reach a certain success rate. So here again, like given a fixed number of data points, you will probably achieve a higher accuracy or success rate if each data point contains information from more modalities. And why do we think that multiple modalities allow us to use less data points? Because they provide richer data and are complementary. So here's an example of what I mean by complementary, that sensor modalities are complementary to each other. And this example specifically deals with vision and touch for the manipulation task of peg insertion. So here in the first part of this peg insertion task, you have the reaching phase, and you see that the force data actually spikes when touching the box. And there's also lots of visual movement that is unconstrained in free space. And then in the middle part, the robot is kind of sliding on the box and the force data oscillates while it does that. And the visual movement of the robot is actually quite constrained. And then at the insertion phase, the force data peaks when inserting and drops finally when it is inserted. And the visual movement is quite constrained, right? Like it's just this downward movement. So really these vision and touch sensory traces have a very specific signature, if you want, for the different phases of this task and provide different information. So at ICRA 2019, we presented a method on making sense of vision and touch that I will summarize here only very briefly. And so in this work, we collected self-labeled data through self-supervision, which takes about 90 minutes to collect 100K data points. We then learned a representation from this data, which takes about 24 hours, but is done fully offline. And afterwards, you can learn new policies from the same representation, doing different tasks, and that only takes around 5 hours of real robot training. And in simulation experiments, we studied how each sensor in this particular work is being used by completely taking away a modality during representation and policy training. So if we only have force data, our policy is not able to even find the box. I mean, obviously it's blind. And with only image data, we get a 49% task success rate, but our policy struggles with aligning the peg with the hole since the camera cannot capture these small, precise movements. And with both force and image, our task completion rate goes up to 77% in simulation. And it's not actually that surprising that learning a representation with more modalities improves policy learning, but our results also show that our representation is using all the modalities for context-rich tasks. And here are also some qualitative demonstration of what the learned policy is robust against. And so here we have Michelle actually pushing the robot around while it's doing its thing and trying to insert. And the arm is actually totally able to recover from these external pushes to the arm and will eventually insert. And here we have a different perturbation of Michel actually touching the force torque sensor and corrupting this data. And you see that the robot does get somewhat confused by this and actually lifts off, although it shouldn't, right? And eventually it will still insert the peg. And then here's the last example of perturbations of the sensory data by Michel, basically occluding the camera intermittently. And yet, despite this perturbation that wasn't at all in the training data, the robot can still insert. So these were some qualitative results, but we haven't really looked at how to more systematically deal with the loss or corrupted sensors. And so this is what I'm going to focus on today. So, so for humans, of course, these kinds of things are always easy, right? So even when one modality is noisy or missing, humans are still able to accomplish amazing feats like dexterous manipulation. And we can blindfold ourselves and still rely on our other senses to help us accomplish tasks. This ability is also known as cross-modal compensation. And the question we asked in this main work that I will talk about is how can we endow robots with the same ability? So here's an example of a robot trying to fasten some wheel nuts, which was a task in the DARPA Arm Robotics Challenge. And now suddenly someone turns off the lights. However, the robot actually doesn't know that it doesn't have access to vision anymore, since the RGB camera is still streaming data. So if we want robots to be able to perform cross-modal compensation, so using one sensor to compensate for the loss of another, we will need to give it the ability to detect when a sensor modality is missing or corrupted. So there have been several recent works in machine learning that can handle missing modalities when doing inference by using deep generative models or training with missing modalities. Previous work has also explored cross-modal prediction of one modality from another, such as predicting vision from touch and vice versa. While these algorithms can handle missing modalities or do cross-modal prediction, they need to know what modality is missing in advance, which, as I just mentioned with the example where the light is turned off, is often not the case in robotics. Bayesian frameworks, specifically recursive filtering, have been used in many previous robotics works to fuse multimodal sensory inputs and can take into account sensor noise and uncertainty. However, traditional filters require users to identify and define analytical forward and measurement models that may be hard to specify or are intractable to compute online. So in this work, we use 3 sensors, an RGB image sensor, a depth sensor, and a wrist-mounted force torque sensor. We assume that during training, all the sensor signals are normal, uncorrupted. However, during deployment or test time, it's possible that a sensor can break. The cameras might get knocked over or become occluded, and the force sensor might break or start drifting. And assuming that only one sensor can be corrupted at a time, we introduce our algorithm that we call cross-modal compensation model, or CCM. And CCM can compensate for corrupted sensor inputs in 3 steps. Given our 3 sensors, image, depth, and force, the first step that CCM takes is to detect. In this example, CCM detects that the image is occluded. CCM then rejects and discards the corrupted image input. And lastly, the depth and force data enters the CCM fusion model, which corrects for the rejected image information. We will now go over how CCM is able to correct for rejected modalities. So CCM is a representation learning model that takes as input an image, depth, and force, as well as robot state. Our input modalities are fused together in a latent representation, which we will refer to as Z. So to teach CCM how to correct for rejected inputs, during representation training, we randomly drop out sensor inputs to generate our missing modality, latent representation, Z prime. we introduce a latent distance objective that minimizes the distance between the full modality z and the missing modality z prime. This distance objective will allow our representation to learn how to correct for any missing modalities by forcing the representation to shrink the distance between z and z prime. We also train CCM using self-supervised objectives from the first work I presented and that we found to be important for representation used in manipulation tasks. Lastly, and this will be important for actually detecting which input modalities are corrupted, we reconstruct our input modalities, a commonly used training objective. And the role of these reconstructed modalities is to help us to detect when an input modality is corrupted. So this is something I will explain next. We only train our representation with normal uncorrupted data. And so CCM is able to reconstruct normal image data with low reconstruction error. However, if CCM receives a corrupted image during the deployment, there will be a high reconstruction error, which we threshold to detect when an input modality is corrupted. And after training, we freeze the representation and train an RL policy. We use a peg insertion task, again, to experimentally evaluate how well CCM has performed. Again, during policy training, we assume that no input modality is corrupted. After policy training, however, now it becomes possible that a sensor modality might get corrupted during the robot deployment. In this case, in this particular example here on the slide, this depth sensor signal is corrupted. And CCM can detect the corrupted modality during policy rollout. During policy rollout using the thresholded reconstruction error, and use the steps of then reject and correct to feed the compensated z prime to the policy. So we showed that during policy rollout, if CCM does not compensate for corrupted images, like the one you see on top, it mostly fails to accomplish the task. So it only has a 29% success rate. If CCM performs cross-modal compensation, though, the policy can accomplish the task 81% of the time, even when the image inputs are corrupted. In addition to corrupted images, we also show that our novel method is able to perform cross-modal compensation on corrupted depth and force data with task success rate of 82 and 78% respectively. We also compare our method to a VAE, a variational autoencoder, with an added latent distance loss, but that does not use the self-supervised objectives for representation learning. And we see that it does not perform as well when inputs are corrupted. So here are just the lessons that we learned from this. Jointly learning self-supervised and reconstruction objectives helps with policy learning. The latent distance loss is the key ingredient here that enables this cross-modal compensation. And CCM outperforms all other baselines by learning how to detect, reject, and correct for corrupted inputs. So just to conclude, just the main core messages of this talk, for manipulation robots, the sense of touch is extremely useful, especially in combination with vision. And how to fuse multiple modalities is an area of active inquiry with many open questions. And here in this talk, I showed you a representation learning method that enables the robot to still perform its task despite a failed sensor modality. And one of the open questions here is, of course, like, how can we scale this up to many different manipulation tasks? And how can we recover from any failure maybe online? And with that, I thank you for your attention. I'm thanking all my amazing students in my lab and also the funding sources for my research. Thank you very much.
Perfect. Fantastic talk. So I think we are taking actually the questions during the panel discussion. Jeanette is going to join us for the panel discussion after the next two talks. And I invite all the attendees just to add questions if you want to the chat, such that we can keep track of the questions for the panel. And it's a great pleasure to introduce our next speaker. Our next speaker is Professor Claire Tomlin. She's professor at the University of California, Berkeley. And today she's going to talk about assuring behavior of autonomous system with learning-based perception in the loop. Claire, I see your screen. Take it away.
Thank you, Luca. And just because of the trend, I changed my title to have kind of a 3-word thing before the colon.
Well done.
You know, just for fun. And I'd like to thank Samuel and Varun, who really did most of this work. Samuel just graduated from my group. Varun just finished last year. Saurabh Gupta, who was a PhD student with Jitendra Malik, and he's now a professor at UIUC. And then this work is in collaboration with Alexandra Faust at Google and Jitendra Malik, who's my colleague at Berkeley in computer vision. Okay, so seemingly straightforward problem, right? This is navigation. So the question that we set out to ask, or sort of embody the problem we were working on in this question, is one of indoor navigation. So we'd like this robot to go from a known position that it's in to a known goal through an environment that it doesn't know. So it knows its own coordinates. So we're assuming that odometry, we have odometry, so we're not solving the odometry problem. And we know the origin, we know the goal, but we don't know what's in between. And it's got an RGB camera, and it needs to navigate from its origin to its goal. Okay, so let me just set this up. So this is a paper that we published a couple of years ago in Coral. So we proposed an architecture, and this is an architecture which is kind of more traditional from control point of view, right? You have perception, which is maybe not so traditional, the module that we're using. It is becoming so now. So that's our learning-based component. But the perception module takes a series of images once every H time steps, and then it provides a waypoint. And then that waypoint, this is traditional, right? It's fed into a planning module. And here we're just using a spline, a third order spline. So we're trying to use like really straightforward, simple components. And then the output of the planning module is a desired trajectory, which is fed into a control system. And that's just a linear quadratic regulator. We assume we know, as we often do, the model of the system we're trying to control. So it's just this fourth order model. And then, it proceeds applies that control for this H time steps, and then feeds an image back into perception. Most of the work in this project was, as you might gather, training the perception module. And we trained the perception module completely in simulation using optimal control. So we used, for training, we used the Stanford indoor 3D data set. So it's called Stanford 3D Indoor Spaces, which is a database with textured meshes. And it's a number of buildings at Stanford, sort of, indoor corridors, lab buildings, etc. The location and the shape of the obstacles then are known from the, in the training. And then in the training, we set up a cost function, which was the sign distance to the target and then away from obstacles. And the goal was to find a waypoint such that the resultant spline from the planning module minimizes the cost. And then that, so trained completely in simulation, and then we held out some of those simulated spaces to do testing on. One of our goals here, this was 2019, so a lot of people were working on end-to-end learning, going all the way from images to the control input to the system. And one of our goals here was to kind of explore that comparison between a model-based navigation system, which uses learning for perception, but then uses the model for planning and control, with a fully end-to-end learning scheme, which has a learning-based system all the way from the image input to the control action. Maybe another couple of details. We're using a ResNet 50 architecture. We trained it using 35,000 iterations, so fairly standard. Okay, so we were able to kind of demonstrate the advantage of using a model-based method over something like end-to-end. And here, this comparison in red is our algorithm as compared with an end-to-end learning scheme. So in terms of the success rate, we had like an 82% versus a 56% for end-to-end. And then of those that were successful in both, the bottom three bar charts show things like time taken to reach the goal, average acceleration, average jerk, right? And these are kind of what you would expect because we're using a model-based scheme, right? We know the model of the system, so why not use it for planning and control? And then these are like tabulated some comparisons. And something to note here, maybe, just we'll come back to this later, is that if you compare our, this is our learning-based waypoint navigation with the, say, more traditional mapping-based methods. So for example, you know, SLAM-based methods, when you're including both depths and spatial memory is great, right? And this is all, so this comparison is on those held out simulated spaces at Stanford. All right, so where did, you know, where did it do better? Like what was kind of the key in doing better than end-to-end? Well, we found that end-to-end really struggled when you had to go around sharp corners, for example. So it would tend to fail when it needed to take a fairly sharp control action to be able to turn a corner, and it would kind of bump into the obstacles. Whereas our scheme, because it's using a, you know, a planner and a controller, which is commensurate with the model that we have, tended to do better in that. So that's not really surprising. And then you can see the comparison in terms of our method, model-based versus end-to-end. You see a sort of less jerky velocity that we observed. Okay, so then we took that, that algorithm, which was trained fully in simulation at Stanford, and we applied it to the actual robot in our lab spaces at Berkeley. Okay, so Berkeley is a little bit different than Stanford. And this is, you know, you can see some of the demonstrations. So it's important to note that the camera images, the thing that the robot's seeing is just that first person view at the bottom left. But just for visualization, we have both kind of an overview at the top right, as well as the bottom right, you can see a third person view. Okay, so again, it knows where it is, it knows where it's going, but it doesn't know what's in between. Here you see that sort of third order spline action coming in. And just a couple of other plots or a couple of other experiments. Here, you know, it starts out inside a lab and its goal is outside here in the hallway. And so it's, again, you know, this is what it's seeing, first person view. It recognizes through the training that this, to be able to get out into the hallway, it has to go through a door to get out into the hallway, even though it wasn't explicitly trained on that. It comes out, comes into a shiny floor where there's some, as you see, there's a little bit of glare, and it does very well even in the face of that glare. And then this is a third experiment. Even though the algorithm was designed just for static obstacles, we tried, you know, this experiment where Varun is here moving that chair around, providing a, you know, a dynamic obstacle on a slow time scale. So you can see the robot kind of trying to get to its goal and, you know, a chair being put in its path as it's trying to get to its goal, but it still manages to get to the goal. Okay, so those are the hardware experiments. And now if we look at that, a similar kind of table, we see that this model-based, learning-based waypoint navigation, our scheme, does really well, even compared to the SLAM-based methods. So this is where, you know, learning-based perception is really shining over SLAM-based methods, because things like, you know, glare on the floors, or, you know, like little water droplets on the camera, those, it appears to be very robust to those issues. Okay, so some lessons learned here. The first is that, the data representation is important. Having a body frame for the representation of where the robot is and its goal turned out to be very important. Another point is that, so we trained this completely using optimal control, but optimal control can be too optimal, right? It tends to skirt corners just to, reach its goal. And then if there's a little bit of error, then the optimal control tends to bump into corners, as we know. So we put, buffers in that. The waypoint representation is also important. So as we showed in that architecture, we had the learning-based module was taking in images and giving a waypoint as an output. How you represent that waypoint is robot dependent. So this is a very simple robot, the TurtleBot, but it was really important, or we got much better performance when we represented waypoint with position and direction, so a 3D waypoint as opposed to just the XY position. And now we're working with one of my colleagues, Kaushal Srinath, who works on walking robots, and then how we represent the waypoint for a walking robot, for example, using this architecture is very interesting. So the waypoint representation is important. Some other lessons learned, we're building on existing neural net architectures. So again, a ResNet 50 that is, a sort of standard trained already on, standard computer vision pipeline for indoor spaces. Image and perspective distortions, it's important to include that during training. And also a point that I want to raise is that we tried to improve this method by incorporating a reinforcement learning. So after training, using reinforcement learning on already supervised learning. And we couldn't get it to improve, which, I'm still kind of struggling with trying to understand that. Okay, so here's where, it didn't work. So here's, it only worked 82% of the time. So what are some of the failure cases? So here, the chairs at Berkeley look different than the chairs at Stanford. So here it was kind of going around that chair and it hit the base. So we started to think how, and I think, to the topic of this workshop, how we might try to robustify these, this perception module in order to feed it through planning and control in a robust way. And so one of the things that we've been working on, and I'm just sort of in the interest of time, just showing our architecture here with this safety verifier. So this is something that we added in. Our group has been working for a long time on safety-based control using Hamilton-Jacobi reachability. And what we did in this architecture was we actually introduced a SLAM-based pipeline from the robot's viewpoint to be able to, from the depth camera, see where the obstacles are just from its current viewpoint, and then compute a reachable set of area to stay within so that it doesn't hit the obstacles. And let me illustrate that more with, that same experiment now including this, this reachable set. So again, the same images as before, but here on the top right image, you see our current representation of the reachable set in red. Okay, so what is this reachable set? It's the set of states that the robot can be in and still stay away from the obstacles. So you see, for example, and it's being updated in real time as the robot moves based on its view of the obstacles. Okay, so let me just hit the movie to go. You can see that as it starts to move, it gets more information as what's around the corner. It comes, close to this obstacle here, and the reachable set and the control that's computed as part of the reachable set guides the vehicle away from that obstacle and around into the region so it can reach its goal. Okay, this is, it's an interesting add-on, or maybe we call it a safety wrapper. It's by no means a solution to robust perception, but it's an interesting question of how you might use multiple sensor sources and control tools like safety-based reachability to be able to robustify perception. Okay, so I put up these kind of challenges as part of our, we're going to have a panel in a little bit. So this idea of a monitor, I'm interested in how we might incorporate a kind of monitor into the perception process to ask questions like, as we're getting this image data, is it in the distribution that we've been trained on? Can we sort of recognize that this is in distribution or out of distribution? And then how do we apply the appropriate control action? The second question is, how might we characterize the uncertainty around the output of the perception module? This is something that we've been working on a lot over this past year with Google, and trying to, we could compute a variance, for example, and use that, but what's the best way to do that in different applications? And then how do you propagate that uncertainty through the decision-making components of planning and control? And then finally, more complex environments. This is a very simple problem, right? I started out by saying that we're navigating in an indoor environment, static obstacles. So we started to work on that, and I'm going to end the talk just by presenting our latest work, which is incorporating humans, which are, as we know, one of the more complex classes of dynamic obstacles. So here's our algorithm that I presented before, but Varun, you see his legs over there. He's going to be walking, and then suddenly he'll walk in front of the robot. And so there's nothing, the robot's not trained on Varun, it's not trained on people. So, it sort of crashes right into Varun. So that's, not surprising. And so we started to ask, well, if we wanted to think about how we might start to incorporate humans walking around or other human behavior, how might we do that? The big challenge, of course, is training. In an algorithm like this that is using, optimal control-based training for the learning-based system, how do we get enough data of people moving around to be able to train the robot and, to act kind of, normally in environments with humans? And so we created this, or actually, I just want to say one more word about that. But part of what might be interesting to recognize is, whether the person is standing still or whether the person is moving. Like, is the fact that their legs are separated important? Are there cues that the robot can take when learning the motion of people? So we created this database, and then we trained our algorithm further, or we trained our learning-based perception module further on this database. So we took the Stanford 3D Indoor Spaces database and we combined it with the Surreal database. We call this HumanAV. And then, so we took from the combination of these, so Surreal allows you to take meshes of people and those textured meshes and kind of insert them into environments. So we created meshes of people and we inserted them into the Stanford 3D Indoor Spaces. And then the input to our database is the robot state. We can also input a human state and control, so we can, move those human beings around the spaces. And then we also have some control over the human identity, gender, texture, like clothing, skin color, facial features, and body shape. Okay, and so then the output is, you can see here in terms of the output, the sort of setup with the human and the robot, the placing of the human in the spaces, and an indication of the depth, how far that human is away. Okay, so after retraining, so creating this database and then retraining our learning-based waypoint navigation, including the dynamic human data. So we have a DH for dynamic human. This is that same experiment. And you can see that as Varun cuts in front of the robot, so this was, sorry, prior to training with dynamic humans. And then this next view, this is cut off with the zoom tab, so I can't see the title. We have the dynamic human. So we see the robot veering to the right away from Varun. Okay, so recognizing that there's some motion and somehow recognizing the direction of motion. Okay, so let me summarize. We've been working on incorporating perception in the control loop. Our method has been to think of a modularized structure where we have a perception, planning, and control. And moreover, we've been training the perception module using supervised learning using optimal control. We compared it with a more traditional SLAM pipeline as well as an end-to-end learning pipeline, and we applied it to this vision-based navigation task. We talked about a safety wrapper via reachability, and then finally we're working on this incorporation of human data. And we'd like to thank our sponsors, DARPA Assured Autonomy Program, the SRC Conics, ONR Basic Research Challenge, and NASA. Thank you very much.
Thank you, Claire. So yeah, we will be taking questions during the panel session. So if you have any questions that you want to ask Claire, please stick around and feel free to use the Q&A right now, and we'll mark them to be answered live as they come up. So great. All right. So Larry, you're up next. Larry Matthews, Senior Research Scientist at Jet Propulsion Laboratory. Your talk will be, and he will be giving a talk on terrain relative navigation for precision landing on Saturn's moon Titan. Notably, not a 3-word punchy title, but that's totally fine, Larry. But if you could try sharing your screen, then let's take it away.
All right, thank you. Can you hear me?
I can.
All right. Let's see here. Looks like I need to get into system preferences and allow Zoom to share my screen. That'll take just a second here.
No problem. You haven't been on Zoom just continuously over the past year, Larry?
Well, we use WebEx. I've been on Zoom, but I think
it looks like it worked.
Yeah, there was some confusion with our IT people who told me to get a loaner laptop, which was probably completely unnecessary. Anyway, thank you very much for the invitation. I appreciate the chance to present this work here. This is work that was funded by the NASA Coltech program. Actually gave this talk at the ICRA Aerospace Conference a year ago. So I was the PI, all the people listed there did all the work. So I want to acknowledge all their contributions. If you've been following what's been going on Mars, we had an enormous success with precision landing on Mars with what we call terrain relative navigation, using descent imagery to estimate the position of the spacecraft while it was still 3 to 4 kilometers above the ground. It did that with an error less than plus or minus about 40 meters. And that allowed it to land at a place that we had already scouted out as being safe using orbital imagery. And it could, I don't actually have the final landing error on my fingertips, but let's say less than plus or minus 100 meters or so. And that was within an ellipse that was less than roughly 20 kilometers long. That was the dispersion propagated down from atmospheric entry. So we could do that on Mars because we have very high resolution orbital reconnaissance up to 30 centimeters per pixel. It's a very clear atmosphere, well, pretty clear atmosphere. And we can use a descent camera that is in roughly the same spectral band as that orbital mapping imagery. Titan is a very different problem. The atmosphere is much taller, it's very hazy, we can't see the surface very well, either from the top of the atmosphere or until within the atmosphere till we get very low. Therefore, the orbital map resolution is far lower, order of a kilometer, give or take, potentially several kilometers. And the sensors that we can see the surface with from above the atmosphere aren't necessarily in anywhere near the same spectral band as the sensors that we can see the surface from within the atmosphere during descent. So we potentially have a multimodal registration problem where if we want to estimate where we are on the way down, we've got to match fairly different sensor characteristics. So this talk is all about coming up with an approach to solve that problem. Now, just a word about time frame for this. with the Dragonfly mission being built to go to Titan, scheduled to arrive in about 2034 and operate for at least 2 years, it's likely to be decades before there's a chance to actually use this capability on Titan. There's a lot of work left to go. Means it's a great problem for academic research. So if anybody's interested in this, there was this paper and a companion paper on guidance and control at IEEE Aerospace last year. Take a look at those papers, write some proposals. Feel free to get a hold of me. I'll be happy to help you, collaborate with you. Okay, so I used a lot of time on that. Here's a sketch of how things worked for Mars. We enter the atmosphere at 250 kilometers above the ground at a shallow depression angle. We spend about 4 minutes on the heat shield. We do bank angle control, which gives us this 20-kilometer uncertainty ellipse at touchdown. We drop the heat shield at about 10 kilometers. At about 4 kilometers, we start taking imagery so we know where we are. And then once we got down to 1.5 to 2 kilometers, the propulsion system could carry the rover to that precision landing I was talking about. So I already talked about this is enabled by having high resolution reconnaissance imagery. For Titan, basically I already sketched what the challenges are. We enter the atmosphere much higher, around 1270 kilometers. It's a very hazy atmosphere. We deploy the parachute far higher, so around 150 kilometers. And then it's a very dense atmosphere. So you have a very long hang time, 1.5 hours or more to get to the surface. And while you're hanging on that parachute, there are fairly high winds. And of course, we don't know those winds very well. So you end up with a pretty large a priori landing ellipse. Huygens was about, the Huygens lander ellipse was about 400 kilometers long, 3 sigma. With some changes in the architecture, you can get that smaller. It's going to depend on exact design of the mission, but the very best we could do, your major axis would always be at least 100 kilometers long. I think for Dragonfly, it's about 175. I didn't look it up, but it's on that order. So that's the challenge that we're facing. If you want to do precision landing, you've got this long hang time with high winds. So you've got this large a priori error ellipse. You can't see the surface and you get relatively low, and then you've got lousy reconnaissance imagery. Why would we care to do this? Well, I won't really take time to belabor it, but there are things that we'd like to land close to. And if we had about 100 kilometers of divert range, in principle, we could actually do pinpoint landing pretty much anywhere, even given all of the problems I just listed. So we need very large divert range. How can we get that affordably? This slide kind of summarizes all the challenges that I just mentioned. Since I've talked about these, I'm not going to take the time to read through this slide. I will maybe call out a couple things. So the row on orbital imaging, if you look over on the right, it talks about what the options are for the map. We can either use a radar map, which best resolution is about 350 meters per pixel, but you only have that in a few places. Or you have orbital imaging in a narrow spectral band in the near infrared around 938 nanometers, or shortwave infrared between 2 and 5 microns. And it turns out the best selection there is a band around 2 microns. And there, the maps, well, in those 2 bands are between a kilometer per pixel or up to about 3 kilometers per pixel. So what we looked at for getting that large divert range is guided parafoils. On the left is an example on Earth where you can get glide ratios, around 5 to 1. Our concept on Titan, we worked this with a company called Airborne Systems. We thought we might be able to get a glide ratio around 2.5 to 1. And so if we could get 2.5 to 1 and start at around 40 kilometers altitude, we could get that 100 kilometers of divert range that I said we needed. So that was the concept that we were working on. So we call this the ConOps diagram. The idea, some of this will become more clear a little bit later, is that we have a radar altimeter. We start to get our altitude around 40 kilometers above the ground over on the left. We know our 3-axis orientation quite well from a navigation grade IMU. So all we have to do is estimate our 2D position, because we can get altitude and orientation. So we take images, we match those to maps, and then now we know where we are. We deploy our parafoil. We can aim toward the target. Combination of map matching and feature tracking until we get close to the ground, and then do some kind of parafoil flare to, reduce our horizontal velocity. There's some unsolved problems about how you shed that horizontal velocity with a parafoil when you get close to the ground. So that's an area for more future work. So the sensor architecture that we envisioned is like this. You've got the navigation grade IMU that's giving you, critically your heading, but also your tilts. We can do a radar altimeter to altitudes above 40 kilometers. And then exactly where you can start doing map matching, not entirely clear, but we chose about 40 kilometers as reasonably credible. And this is limited by the haziness of the atmosphere. And so then you've got a couple of options. You can take descent imagery and try to match them to a map. And that's meant to be illustrated by that reddish figure there, which is actually a mosaic of Huygens imagery. And it's pretty blurry when you're up around 40 kilometers. Or if you can actually recognize specific features, you could perhaps just navigate relative to those. You don't have to do absolute position estimation. And one specific feature that is a good example of that is the methane lakes and seas, because they're very highly absorptive in these longer wavelengths. So as long as you're not near a specular angle, it's probably a fairly easy problem to segment the descent imagery to find those lakes. And then if you want to land in the lake or land near the lakeshore, you can just navigate relative to those without knowing where you are. So there's a couple different paradigms. Now, as we drop in altitude, we have combination of problems. One is with the low resolution map imagery, it's going to be harder to do map matching because you just don't have enough resolution in the map to have the footprint of your descent sensor is small relative to the map pixel. Also, you've got two things kind of working in opposite directions. As you get lower in altitude, there's not as much scattering from the atmosphere to reduce the contrast of the imagery, but you've got less overall light. So your images are getting darker. So that's a problem. I'm going to have to start probably going even faster through this. So this tries to capture what are the constraints. So the atmospheric haze puts an upper bound on the altitude at which we can start map matching. The low map resolution puts a lower bound at which we can do map matching. There's a few options for what the maps are, either the near infrared maps or probably the radar map. And then we have this multimodal registration problem because the best descent imagery for part of the descent is going to be shortwave infrared around 2 microns. So we're going to have to match 2 micron descent imagery to either a near infrared map or a radar map. And so we looked at different approaches to this. We looked at normalized cross correlation or mutual information when we're over dry ground. And then there's a region that's of scientific interest where there's a lot of small lakes where we thought we could binarize both the radar map and the shortwave infrared descent image and reduce this to a binary correlation problem because there's so much contrast between the lake and the terrain at that region. And so, as I mentioned, in principle, you could also do navigation relative to recognizable features like the lake shores. Okay, so we did some radiometric modeling to look at the signal noise ratio of both the signal we call direct coming directly from the surface and the diffuse scattering from the atmosphere. And this attempts to give you an idea that you got better direct to diffuse ratio in shortwave from all altitudes, but as you get close to the surface, you just don't have enough light. So we felt that there's going to be some transition point, which we picked as about 20 kilometers, where you switch from doing above that to do map matching with shortwave infrared. Below that, you switch to using the very near infrared. Probably can't do map matching anymore, but we could do feature tracking. So the paradigm here is do map matching for the first part of the descent and then do IMU, visual odometry for the rest to bound your drift. And so we did some experiments discussed in more detail in the paper with Monte Carlo simulations to give us a noise model for both the map matching and the feature tracking, so that we could then do Monte Carlo simulations of a navigation filter, which is the MSEK EKF, to assess our navigation error during descent. So we assumed our map would be the 938 nanometer global mosaic with a resolution of about 2.8 kilometers per pixel. There is a shortwave infrared global mosaic that we used to generate synthetic descent imagery. And then also we had a second case where the map was the radar resolution. So we did Monte Carlo simulations of matching shortwave infrared descent imagery to either the near infrared map or binarize them both and register to the radar map. So what we found is that when we could binarize, we got the best results. One sigma matching error below 1 kilometer per pixel. And when we're matching to the near infrared map over dry ground, interestingly, normalized cross correlation did better than mutual information. And our 1 sigma errors were around 2 to 3 kilometers per pixel, 2 to 3 kilometers. Okay, so then for feature tracking, over on the top left is an illustration of the low contrast problem we have because of the atmospheric scattering at higher altitudes. As we get to lower altitude, we're not looking through as much haze. We can get better contrast. There's not very much relief on Titan. So what's working for us is we can use very large feature patches because there's not much relief. And as long as we know our heading pretty well, we can do that to try to overcome the noise. So again, we did a bunch of Monte Carlo simulations to create a model of what would be the tracking standard deviation as a function of altitude. It gets better as you go to lower altitudes. And then we plugged those error models into a Monte Carlo simulation of the navigation filter. So we assumed we would start map matching at 40 kilometers above the ground. I don't remember what frequency of map matching we assumed, but some frequency, a minute per frame. We're going to spend for that part of the descent, I've forgotten, maybe a half an hour. And then we said, okay, let's just assume that at 20 kilometers, we stop map matching and we switch over to feature tracking. And we simulated tracking some number of features and a navigation IMU, and then looked at what dispersions do we have in our position knowledge when we get to the ground. So here we show one trace in the blue line and then the 3 sigma error bounds from the filter. And the bottom line is it looked like we could get 3 sigma error on the order of a couple of kilometers at the surface, which would be fantastic if we could achieve that. So conclusions, we think it is viable to do map matching from somewhere around 40 kilometers down to 20 kilometers using a descent camera in a narrow spectral range around 2 microns. That's because we minimize the results of scatter. But when we get below roughly 20 kilometers, those images get too dark. So then we have to switch to some other strategy. So what we evaluated here was feature tracking with the very near, for Titan, because of the way scattering works, you got really high scattering in the middle of the visible band. But as you go to longer wavelengths, so the Huygens descent camera was filtered for 660 nanometers to about 1 micron. So you want to use a descent camera somewhere in that band. I think what we simulated was 500 nanometers to a micron. And we think we can do feature tracking in that range to bound the position drift while you're descending without being able to continue to do map matching. And we think that it looks like a 3 sigma error on the order of 2 kilometers looks viable when you combine all these things by the time you get down close to the ground. And I think, I'm not sure if I'm out of time, but I'm pretty close to out of time. So I'm done. Thank you for listening.
Thank you, Larry. Great talk. Very interesting to hear about this too, because it's in a very different application domain than some of the other ones, and also highly risky, it feels like. So thank you again. So now we're going to move to our panel discussion. So if Jeanette and Claire could join us. And Jeanette, thanks for your talk again. Glad that I could thank you live. So now we did have a few questions come up over while the talks were going. So I'm going to first start with a question for Jeanette. So Jeanette, is there a performance gap between training on 3 sensors and only having 2 sensors available and just training for 2 sensors? And if so, how large is it? Was a question from Herman Bloom.
Good question. I don't know. I don't think we have tested it. So just generally, I guess I like having more sensors than fewer sensors. But honestly, I cannot tell you right now what the training speed is. I don't know. We are often using self-supervised or unsupervised training objectives. So in that sense, there is no additional work on, labeling stuff or whatever. But yeah, in terms of training, I'm not sure.
Sounds good. Herman, if you have a follow-up, feel free to put in the Q&A. I had a question actually connected to that, Jeanette, I think. So when you were evaluating the vision versus tactile information content, and you were sort of doing the test of corrupting one versus the other, right? You were throwing the red piece of folder in front of the vision, and the vision, it was able to sort of recover. But if you pushed the tactile one, then it did recover, but it took longer, and it seemed like it was more catastrophic in some way. And I was curious if you have any idea about how this relates to the type of sensors these are, and whether there's a general thing, something we could take away from this, or whether this is sort of just maybe an artifact of how these 2 features were being sort of composited with one another.
Right. So I think the most common question I get on this first work that I presented in the talk is, so how are exactly these modalities used, right? And we don't really have we didn't have a way to introspect that in that sense, right? We only have these empirical results where we can show, if we take that modality away, then here's how bad the whole thing suddenly becomes. The qualitative results on the, perturbing the input. Yeah, I mean, in a way, I would say the robot kind of did the right thing, right? Like it received like a force signal that told oh, I'm feeling way too much force basically on the end effector, so I should probably back up. And it did recover in the end, right? If you left it as is. And then the other one was just intermittent perturbation, which kind of, honestly, it's a bit like a tea, how do you say that? Like when you look into a teacup and you read the tea leaves.
Reading tea leaves,
yeah. Honestly, I don't even want to speculate exactly about what is going on or what does exactly tell us, because it's really hard to interpret these networks. And that maybe leads to another question, which is, what do you prefer? Having a network that has a learned latent representation, or do you prefer a network that has an explicit state representation? It can still be a network, but it maps into that space that you actually understand. And I think often that latter part is more preferred, because then you can use that interpretable representation to maybe put bounds on things or check for safety. But you may just lose some information by compressing it into this given representation, right? But you gain interpretability. It's a question I don't have an answer to, which one to pick. Yeah.
That actually leads me to a question that I wanted to ask of everybody, which I think may dovetail with one of the Q&A questions that was asked. So this was originally going to be directed at Claire, but I think, Jeanette, you kind of opened the door. So Claire, you sort of mentioned safety in a place that is a position with robustness, I think. And I'm interested in, like how we can, so everyone here chose their talks for a reason. This is the robust perception workshop. And, like, I guess everyone is sort of focused on robustness in a different way. And we didn't define it for you when we told you how to choose your topics. And I'm curious how you see the interplay between safety and robustness. And Jeanette, I guess your question would be, robust, like what is robustness in general, and does explainability come into that? And Larry, I guess you may have a different take than Claire and Jeanette on what robustness means in this context, but Claire, maybe you could open it up.
Yeah, I mean, I think this is more my perception of it, but I think about robustness in the perception module leading to safe operation of the system. So I was quite explicit, or in the kind of control work that I do, I'm quite explicit about safety. It means, you specify it. It's typically satisfying constraints, and those constraints are specified ahead of time, or they could be learned. But the system is safe if it satisfies these constraints. So now the perception module, we have to have enough confidence in it to be able to try to characterize the output of that perception module as being trustworthy, so that we can then guarantee the safety of the system. And so I kind of think of robustness as a characterization of the output, or the input-output properties of the perception module, leading to being able to make safe decisions about the operation of the system.
Thanks. Larry, do you have any thoughts on that?
So I was thinking about the question that Tim had in chat when you asked the question. So the question is, what do I think about robustness in perception?
Sorry, I didn't mean to. Yeah, basically, okay. Yeah, I was reading Tim's question as you were saying. So yeah, I mean, my question would be, like, so it sounds like Claire's definition of robustness is, it's processed through the transfer function of action to relate to safety. If I could, well, yeah. And so Claire, I might be mincing your words here. I'm sorry about that, but yeah,
no problem. So my top level thoughts about robustness is, everybody knows that perception is really noisy. So, philosophically, you overcome noise in the perception system through, two main techniques are redundancy and multimodality. So redundancy is, all the history of work on better outlier detection. So we track many features because we know that the outlier distribution is pretty bad, and we want to pull the inliers out of that with great outlier detection methods. And then multimodality overcomes weaknesses of each sensor type to get a sensor suite that ends up being robust in the environment. And so, how to formalize that or quantify that, think of it in statistical terms. So, whatever quantity you're trying to estimate at the end of that, you want the bias and the precision and the outlier distribution of that output to be within whatever bounds you need, given that enormous noise distribution on the front end. And you get that through redundancy and multimodality. How's that?
Can't argue with you. It sounds good. Jeanette, do you have any thoughts here?
Yeah,
anything to add, I guess.
That also sounded good to me, what Larry just said, for sure. I completely agree with this multimodality and the redundancy for robustness. Although I couldn't answer your question on actually interpreting exactly like how this is working in that learned system. One thing that is, I just wanted to mention, maybe in response to what Claire also said, typically I'm very dissatisfied with the generalization abilities of these perception models that we learn. They typically only work in the specific scenarios that they are trained on, right? So this is specific for learned models. One thing that was interesting in that work that I presented in the second part of the talk was that this overfitting problem was actually a feature of this work rather than a bug. So by using this autoencoder that actually reconstructed the input and comparing it to the input, we could see that when something is out of distribution, out of the training distribution, and therefore just get rid of this input, and then exploiting the redundancy in the system through multimodality to still achieve the task with the robot. So there we achieved robustness by being able to decide what is the current input in our training distribution. If not, we get rid of it and try to compensate with the other sensors for this. So that's also a different way to how to look at robustness in learned systems specifically, where suddenly overfitting becomes a feature.
Yeah, I mean, in that safety-based work that where we had a safety filter and a reachable set, the multimodality is exactly what we were using. So we had the RGB camera, but we were taking, we were feeding that into our learning-based perception module, but we were also taking sort of mimicking a depth-based camera by looking at the differential between time shots of the RGB camera to create a SLAM pipeline. And so we had those two pipelines running in parallel.
Cool. I think maybe we can ask a couple of questions that have been posted on the chat to Larry, and then Larry, maybe you can, I see you're already responding in one of them in the chat, but maybe you can respond on the first one. So Tim Barfoot is asking the following question. First of all, congratulating you about the talk and the concept. What do you think about the key technology maturation milestones might look on the path to flying this mission essentially? And from my side, if I can just add one more question or request actually to this question from Tim, maybe if you can enlighten us about the specific cameras and sensors you consider for such missions, because you mentioned a little bit for the spectral bands, but I'm sure some of these cameras you are using are not conventionally used from the community who attends here. So maybe as you answer this question for Tim, maybe provide us some kind of insight to the hardware used in such missions.
Sure. So broadly speaking, there's algorithm and software issues, and there's hardware issues, which are basically the sensors and the processor. So on the algorithm and software side, we made a bunch of assumptions in this work. We created some models and did some simulations. There's room for us having made errors or not having made the best choices there. So I think there's lots more work to be done on the algorithm side. On the hardware side, the sensors that, well, so one thing I want to add here, we made assumptions about what would be available for maps. An interesting thing to consider is I think there's a good chance that the next mission to Titan, whenever that happens, what seems to make most sense is another orbiter with a new mapping camera. And so that was actually proposed in the last competition. It lost out to Dragonfly, but another orbiter with a new mapping camera could get global maps with resolution of about 100 meters per pixel or better. And that would both revolutionize the science and revolutionize our ability to be able to do navigation during descent. So that's just a bit of context. Now, what hardware do we need in the spacecraft? Well, we need that navigation grade IMU. Right now, the state of the art in deep space IMUs is called the MEMU. That's from Honeywell. It's about 5 kilograms. DARPA has been funding work on navigation grade MEMS IMUs. Other people may be funding work on that get IMUs for Earth applications down to a few hundred grams. So there's possibilities there for miniaturization of the IMU. There was the question about IMU biases. Like I wrote in the chat, we made some assumptions about IMU initialization before entry That probably is another area that needs to be revisited. That's all I'll say about that for today. Cameras. So we assumed 2 cameras for descent. One, basically a standard silicon detector, CCD or CMOS imager, probably bandpass filtered to the near infrared. So 500 to 1,000 nanometers, or 600 or 700 to 1,000 nanometers. Those are pretty, pretty standard cameras. We also assumed a shortwave infrared camera, bandpass filtered to about 2 to 2.1 microns, and that's just based on where the the visibility bands are in the Titan atmosphere. And detectors for that spectral band exist. I don't quite remember what the best option is now, but maybe some kind of enhanced in-gas detector or MERCAD. I don't remember actually what the right detector is, but so those cameras can be done. Radar altimeter. Huygens had a radar altimeter that was designed to be able to detect the ground up to something like 60 kilometers above the ground. They had some glitches. It didn't actually work very well until it was down to, I think, around 20 kilometers, but it's eminently feasible to do a fairly small radar altimeter to work at altitudes up to 50 or 60 kilometers. In all of the years since Huygens, I'm guessing we could do a smaller one than Huygens had. I don't remember its numbers, but it was probably also around 5 kilograms. We could probably do a smaller radar altimeter. And then you need a computer. So, in the space business, cost is a big deal. Mass is a big deal. You want to make things as low mass and low cost as possible. We don't want to have a boat anchor as a computer. So the Ingenuity helicopter is flying a cell phone computer. Actually by now it's a pretty old cell phone computer. I think it was introduced, 8 years ago or so. So the atmosphere of Titan is so dense that we're not going to have problems with radiation effects in the Titan atmosphere. So I think we could fly a recent cell phone computer or computer from the self-driving car industry for Titan descent and probably do just fine and get, compared to what we normally have in the space business, enormous amount of compute power in a very compact package that wouldn't require a lot of power. So the question was really about technological milestones. Those are the main ones. One more that I said we left kind of unanswered here is when you get really close to the surface, like the last kilometer of descent, you got to manage all that. If you go with the guided parafoil concept like we had here, what do you do about all that horizontal velocity? So how do you shed that horizontal velocity, or how do you be robust to the horizontal velocity at touchdown? So that's an open question. So I hope that answered the question. That's about all I have to say about it.
Yes, thank you. Out of just the last question for that, out of general curiosity, what is the anticipated weight for such a platform to enter Titan? Because I think this is part of your constraint also, right? What is the weight and therefore the weight of the sensors and so on?
Great question. We had a model for that in the work, and I think we probably made an assumption that it would be at least as much as the Huygens probe, and drawing a bit of a blank on what that was, but I think it's a couple hundred kilograms or more. So we weren't looking at something. I think Dragonfly is up around 600 kilograms. So I think we were looking at a range between 200 and 600 kilograms.
Cool, thank you. Switching gear now, I think one question to Claire, if you will let us know, give us your insight for the following. So you mentioned, for example, that you recently focused on the uncertainty on the perception pipe part, and I wanted to ask the following. We know in traditional work related, for example, to random belief trees, that people have examined the problem of incorporating uncertainty of photometry into the planning process, right? And I want to ask, for example, since you also try to incorporate the safety verifier that you present at the end, can you share with us some comments about how you could use your not only your odometry mean value, but also your odometry uncertainty, and then provide actions that are guaranteed to be collision free despite, let's say, 1 sigma of the uncertainty L-trade of the odometry?
So we've been thinking about that, and we don't have a solution yet, but we've been trying a couple of different things. One is kind of from a worst case perspective. So as you say, you could take some level set of that uncertainty and then look at the worst case and use that to feed into the planning pipeline to indicate, okay, worst case, I'm indicating that the best waypoint. So for us, it's important to reflect this back to what the output of the learning-based module is. And for us right now, it's a waypoint. So if we were to, and we're calculating kind of the best waypoint according to this metric that I talked about. So you want to minimize your distance away from obstacles, but maximize your distance towards the goal. Sorry, the other way around. You want to get to the goal, but maximize your distance from the obstacles. And so you could calculate, what would be the range and possible waypoints, and try to ensure that any plan that you could come up with, so even in the worst case, waypoint, that you're going to, that plan will still give you a conflict-free action. But I think this is kind of a specific focus on our particular problem. In general, I'm interested in the stochastic, a kind of stochastic optimal control framework, which will take that variance into account in a meaningful way and give you probabilistic guarantees in that case on the behavior of the system. And that would be a framework which could then be applied to, waypoint or to obstacle detection or classification. And I think that's, it's an area that more and more people are working on, but I do think it's something that there is going to be quite a lot of work and quite a lot of, advances made in the near future, just because it's so important given this way we're now modeling and characterizing sensors using these learning enabled components.
Right, thank you. And then kind of more detailed question from one of the Q&A. Can you elaborate a little bit on how a reachable set is combined with control to achieve obstacle avoidance? So this was posted maybe to provide some insight to what the paper says.
Yeah, so we again, we have our one sensor is an RGB camera. So one channel, we're using the RGB camera, as I said, through the perception module to give us a waypoint. In a separate channel for that reachability work, we're using the differential between multiple time steps of that RGB camera image to produce a depth-based map of where obstacles are based on your current view. And so for each of those views, we treat everything that is unseen as well as everything that we see as an obstacle as unsafe. And then based on the dynamics of the system, we compute a backwards reachable set from that unsafe region. So the complement of that is our safe region of operation. So we use, and for that computation, we use a Hamilton-Jacobi reachability framework, which gives us not only the set of, in that case, a set of unsafe conditions, so we're interested in the complement, but also the control action that you would apply if the robot would apply if it hit the boundary or got close to the boundary to keep it, inside the safe region. So the question was asking about, how realistic can you expand this to 3 dimensions? Do you hit cursive dimensionality? So a lot of the work that we did there was, and this is work by Andrea Baichi, who's a PhD student in my group, jointly working with Anka Dragan. So she worked on this methodology with Samuel Bansal, who is one of the co-authors of the HumanNav and the Waypoint Nav work, on a method for speeding that computation up using only local updates. So if you've previously computed a reachable set, you assume it's not going to change much over the next the next time step, even though you've moved and you've got kind of a bigger, maybe a more expansive point of view, depending on what kind of sensor you're using. And so she used a warm start and just local updates. You just do the computation around the boundary to be able to really do those computations in real time for the models that we had. So yes, cursive dimensionality is always there with these procedures, and the name of the game is really trying to find good kind of either approximation methods where you can still make guarantees of safety, or other kinds of like logical based methods for decomposing the computation so that you can do it in real time. And so she did that for that navigation problem with two kinds of sensors. She used both a camera as well as a LiDAR sensor to be able to see how that methodology would work with those two different kinds of sensors. So it's very much a current problem, and that's one of the methods that we've been working on, and we're integrating into what we're doing moving forward.
Thank you.
So I think that we probably have time for one more question for each of the panelists. And one question that we asked in the first, for the first panel, which gave rise to some of the more, I guess, the kind of the crazy comments that we've had since then about what odometry is still very hard, which is true, right? But maybe you know, people could argue that. It's this question is, what are some breaking points of resilience in localization, mapping, and state estimation, just perception in general, and things that you're excited about? What would be the one thing that you're probably the most excited about, or that you're most concerned about in terms of these kinds of robust perception solutions going forward? And Jeanette, if you want to start, then that'd be great.
Sorry, you asked what applications?
Oh, the question is, you know, yeah, breaking points that you see as sort of like on the horizon that must be solved before we get to, you know, that would make, if solved, would result in a great leap forward for perception, or, you know, maybe certain types of trends that you see in the field that you're excited about, that, you know, you might want to speak to here.
Yeah, great question. I think there are many things that I'm excited about. I think one thing that I kind of accepted, and maybe this very much depends on the kind of task you're doing also, is that failure will always be inevitable, right? So there will always be something going wrong. And it doesn't mean though that you have to fail at the task overall, right? And the question is, can we work on what are methods to recover from failure, or to just maybe not catastrophically fail, what tease out what you actually learned from this failure. Like, you failed, but okay, like that must have told you something about what to do next. And then how do you incorporate that information and move on? So I think methods in that direction will be really useful in certain scenarios, right? Like failure is not acceptable in certain applications, but if it comes to manipulation, for example, when you assemble things, as long as you don't break these things, but you just recover from them, that's totally acceptable, I think. Yeah, and I think the other thing, just algorithmically, that holds us back is generalization and scalability to different scenarios. I think just generally, I think all these learning-based methods, they have some great potential for actually generalizing over many different manipulation, maybe many different object shapes and kinds of objects and tasks. But when it comes down to it, you're just spending you have to collect a lot of data to make something work in a still pretty narrow environment. And I think there's still a lot of work that needs to be done just algorithmically on maybe, yeah, like not learn from scratch, continue learning, and these kinds of things. Yeah, so that's kind of what I'm excited about in terms of that.
Thanks. I'd love to hear from Claire and Larry if you have a few minutes extra that you can spend. Maybe Claire first, if you're okay with that.
Yeah, I agree with Jeanette so wholeheartedly about generalization, having, you know, just I mean, I'm a control person, and having worked on this perception module for years, just like looking at the how you can even try to force generalizability is a big question. I also brought up in my talk about safety monitors. And I don't even know if that's, I mean, it sounds like it should be some kind of metric, which is monitoring whether or not the data that you're feeding into the neural net is in the training distribution. So how do we even characterize the training distribution? These are really challenging problems. So is that the correct way to define a monitor? And then how might we even build such a monitor? So that's something that we've been quite interested in. But I think more generally, it's, you know, when you start introducing learning-based components into control systems, it's not even clear how to define safety, right? Like, so what is the, and maybe robustness too. So what is a realistic notion of safety when it comes to control systems that incorporate machine learning components? We know that the trade-off between safety and efficiency is hard to navigate. And you know, in some application domains, people expect perfect behavior from autonomous systems. So how do we deal with it? You know, should we think about probabilistic failure rates or even comparison to human experts? You know, how do we think about how we define safety is an interesting question to me.
Thank you. Larry, do you have any other thoughts?
Sure, I'll just comment briefly on what I see as 3 open problems. So absolute localization for us, for off-road environments, you know, on planetary surfaces, where you can't solve it geometrically. So you don't have a prior map that lets you just solve it with a LiDAR, okay? Your map is imagery. And the open problem is when you have significantly different lighting between the map and the onboard sensors. So, you know, we're all familiar with that problem on Earth. You know, in space, that's still a hard problem. Second one, most germane to off-road navigation, but that's not the only place that it matters, is compliance. So how do you make a system that understands the spectrum between totally rigid geometry and compliant materials and the significance that those have for where and how you drive? So basically, a perception and reasoning system that understands compliance is in the scene, I think is still an open problem. And complementary to that is the planning and control system that deals with, in an intelligent way, with the limitations of the perception system. For example, when you have a limited ability to understand the compliance in the scene, how do you behave in a way that kind of optimizes the trade-off between speed and safety, or between exploration versus exploitation in a context where you've got limitations in your perception system? So thank you.
Excellent. Thank you, everyone. Larry, Claire, Jeanette, for your time, for your talks, and for your thoughts on these items. So for everyone else, and I'm sure that there would be claps if we were all in a room. So at this point, thank you again. Now we are going to go to just a short break, and then we are going to reconvene in about 25 minutes at 3:30 Eastern time for Sanjeev and Tim's talks, as well as a panel discussion among their talks, and then some closing comments. Thank you again. See you soon.
Thank you. Thank you, Chris and Luca and Margarita.
Thanks, everybody.
Ali, Kostas, thank you.
Bye.
Awesome. I think I'm gonna wait maybe a couple more minutes for a few more people to join, I guess.
Ali, do you want me to set up my slides?
Sure. Yeah, please. Let's share screen, see if we can. Yeah, great. I can see your slides. Perfect.
Okay. Is that good?
Yeah, that's the right screen. Thank you. Yeah, I'll basically start the session maybe 2 minutes.
Sure. This is a very interesting workshop so far. I've been following it. How are the people?
Yeah, we got a really nice discussions, amazing lineup of the speakers. I'm pretty excited.
Tim,
Sanjeev, yeah, good to see you. You violated the title convention.
Which is what?
You were in conformance. You had 3 words before a colon and then the rest of your title, but now you've changed it.
Yeah, I thought, okay, that's kind of boring, right? Yeah. Yeah, I decided to do something kind of different. I
don't know how I'm going to follow this talk. That sounds like an amazing title.
I'm going for breadth rather than depth. I realize that I've actually been holding on to some great data that doesn't get to see the light of the day outside a sort of a small group of people. And I thought I would show that kind of stuff and talk about some interesting flight experiments and testing in these kinds of difficult real world environments, and talk about some principles at a high level. So let's see how it goes.
Awesome.
Well, that's good. I did the same thing, so it should work out.
Great. Okay. So hello, everybody. Welcome to the 3rd session of the Robust Perception Workshop. My name is Ali Aga. I am the leader of the Aerial Mobility Group at JPL, and will be chairing the first part of this session. We're going to have 2 amazing talks, but before I go ahead and introduce the speakers, I want to remind everybody that we are taking the questions in the panel session, panel part of this session. So please, go ahead if you have questions during the talk, add it to the Q&A. You can find the button at the bottom bar of the Zoom window. And with that, so it's my great pleasure to introduce our first speaker, Professor Sanjeev Singh from CMU. He's also the CEO of Near Earth Autonomy Company, and he will be talking about perceptual robustness in challenging environments. Sanjeev, please take it away.
Thank you so much. It's great to be back in the ICRA format again. So I was just saying before I got started that I changed the whole talk itself in the last couple of days, because I realized that there was some data here that I could show that doesn't get seen too often, and it does relate to the topic of this workshop. So I changed it from being a little bit more theoretical to being somewhat more pictures and videos, things like that. Okay. Let's see. So for the last few years, I've been living in an interesting world where I work on large aerial vehicles, not that specific one, but at that scale. And of course, these aircraft are some sort of robots, or they want to be robots, and we'd like them to go into challenging environments. If we're going to have them operate by themselves, then they have to be able to do what human pilots do, and even more than that. So my talk is going to be skewed by this kind of environment and world, definitely from thinking about large aerial vehicles. So not only are we concerned about this kind of situation, which is called brownout, but also whiteout, smoke, fog, rain, darkness. So I'm going to try to give you some sense of the techniques we've been using when we try to automate vehicles in these environments is a very challenging thing. Also pretty risky and expensive to do that. So here goes. Okay, so what I'll do is I'll give you some examples, integrated visual environments with snow, dust, fog, smoke, somewhat sort of thinking out of the box when you have to operate in these kinds of environments. And then I want to talk a little bit about some stuff that came up earlier today, which is degeneracy in the world itself, and that the appearance and the structure of the world lends itself to some degeneracy. And it comes to the point of how do you do robust perception in those kinds of cases. They look pretty innocuous at the outset, but they really actually, you lose some information along some directions of motion. So what do you do with that? I think some of the authors, Sebastian, maybe some others actually talked about it. I'm just going to say a little bit more about it and to complement those things. Then I have just sort of like a takeaway for those people who don't live in these worlds, and like, how do you think about sensors in these environments? And maybe there's a cheat sheet that I refer back to often, like, okay, we're in this environment, what should we do here? Okay, so for many years, I worked on taking that specific helicopter and making it into a robot. We were not allowed to show the data from this for quite a while, but now we can. I think enough time has gone by. The problem in flying this kind of a vehicle is that it has to solve all the problems that any other robot has to, which is where am I and what's around me. Of course, if you can figure out the where am I problem through some sophisticated inertial and GPS kinds of systems, then there's still a problem of what's around me. I want to make sure that the vehicle doesn't run into something and it lands exactly the place it's supposed to land, that sort of thing. So one of the things it's supposed to do, this vehicle had to do, was to come in at a very shallow glide slope, very fast into an unmapped area or a rough terrain area, and then be able to find a landing spot if one existed. So here's the specific kind of task that we were looking at, which was coming in about 100 miles, at a little over 100 miles an hour, about 100 knots, and into this unmapped area, and then building such a map like this on the fly, and doing it without a lot of help from any prior or anything else like this. So the vehicle is equipped with some lasers in the front here, a custom-built laser scanner, which is one axis very fast and the other axis is nodding, and some cameras and IMU registered very, very closely to, everything is all synced very tightly together. And its job is to be able to come in and to build such a reconstruction in the environment and figure out if there is a good place to land. And if not, then to wave off and try again. So, so the key idea here in this sort of thing was that, of course, we built this sort of state-of-the-art LiDAR scanner with custom-built motors and state-of-the-art IMU, et cetera, was that it used two ideas to be able to deal with the kinds of environments. One is that it used a multi-return LiDAR. Now, most of us are familiar with first return and last return, but the very high-end LiDAR give you multi-return, which is that if there is a red beam going from left to right, it hits something, but along the way, it's going to give every return that it gets, it's going to respond, it's going to give some sort of signal, you'll get a range to it, and you'll get some signal strength to that for that return. You also get a sense that you know what the last return is. Sometimes there's no last return because there's no opaque object behind there. You just get a bunch of things that are dust or snow or something else like that. And then the second thing to deal with this kind of environment is to use what we call local shape descriptors, which are ways of segmenting out the point cloud that you get from this, of segmenting out the registered point cloud to figure out what is solid terra firma, what is vegetation, or what is dust or other obscurants. Okay, so here we go. This gives you an idea of the kind of, this is back to 2014. In some of the test flights we were doing earlier, we encountered some precipitation, and then we're able to use this idea of taking some of the last returns and also doing the spatiotemporal filtering, which is actually a learned descriptor, not just sort of separated in space. So what you're able to do is to take voxels of in the environment and look at the points in that and figure out which ones belong to some obscurant. So here it is. I think it's coming in from right to left, and here bottom to top, and you can see it with and without the obscurants, because the low flight actually kicked up a lot of the snow, and I'll show you some video of that. And here you see we were totally unprepared for this. It just happened that when we were doing a fully autonomous flight, the first thing we encountered was a whiteout condition. Not prepared for that, but fortunately, it is possible to be able to filter out some of this in real time. So of course, you know, what you have here is a low pass filter, spatial low pass filter. But what you get if you just run a low pass filter is you get rid of all your high frequency kinds of things. And one problem that we have in detecting one good set of obstacles we have to detect are wires, and wires also are extremely high frequency. So of course you can do some coherence kinds of things, but if you do your if you set up your filtering properly, you can in fact still find the wires while rejecting a lot of the noise. Okay, so you know, snow is one kind of particulate. Dust is something that we worry about a lot, and we actually got involved in a series of impressive dust testing. There's a test range which has a number of objects sitting on the ground, very carefully calibrated, and then a dust wave is created, and then the job is of the perception system is to see what it can see in here. So we did a bunch of these. I thought I'd show you what they look like. Here's an example of what the brownout is and how it's created. So see, this is a pretty serious brownout that's been created on by intention. On the right side here, there's actually a Black Hawk that's flying to create that brownout, and this is extremely fine sand that is is stirred up here. And meanwhile, you got a lot of imagers to see what they can see. So what we find is that if you have moderate dust, you know, the kind of LiDAR we're using with multi-return is able to actually penetrate. You can see on the right side here is the dust, the front end of the dust coming here, and then you can actually image right behind it. Also, these are different kinds of objects that are there. But okay, when it gets to be much more thick, then it becomes more difficult. So here's some of that. What you'll see is extremely thick. On the right is thermal imaging, on the left is just visual imaging. So again, you could see some thermal imagery working, even though the visual image is almost completely obliterated, but thermal works to some extent. Here we have LiDAR now, this high resolution scanning LiDAR. And what you're seeing is at the top a render of the point cloud from the LiDAR, and it's picking up the dust storm, the dust that's coming. And when you get, in this particular case, is the very thickest of the dust. And in that case, there is absolutely nothing that's getting through here. So the takeaway here is that LiDAR will work in, if you can actually get these beams through, there is a hope of something getting through. But if you just basically have such thick obscurant with very fine particulate, well, even that will fail. Okay, so I wanted to show you a question about, well, all right, well, what do you do in extremely whiteout conditions or brownout conditions? What does work? Well, one thing that does work is radio, and we use radio to be able to localize in the smoke. So there's this idea of doing localization from radio, and what you get when you get a range from between two radio tags, so to speak. You can have a transmitter or a receiver, and they talk back and forth and very quickly produce range in between. Is you get this donut shaped thing. So if this was the blue is the one that's doing the measuring, it sends out a chirp, it gets a range, and what you get there is from that one single range measurement, you really get a donut shaped toroid as the evidence that you get from there, just from that single measurement, because you have no sense of bearing. Well, a simplified integration would basically linearize. You don't know which direction you have, so you'd get this big green ellipse given whatever operating condition you had. So say that your previous estimate was at this purple star with some uncertainty. What you would get is then this green ellipse here. And this is actually a very poor, I mean, this is the best you do if you use a simple Kalman sense, which is linearize around your operating point and give some uncertainty, some very large uncertainty in the bearing direction, in the bearing axis. But so this is extremely fragile and of course depends a lot on the initialization. So this is a while ago. What we did was Joe Jugash and I were working on this to come up with a representation in a dual space in a polar space where the toroid is translated into an ellipse at the range with the uncertainty, with these sort of tails that go beyond 0 and 2 pi. And what you get is you get this sort of like wraparound kind of funny looking ellipse. And now what happens is you basically do your merging of your data in this polar coordinate, and it turns out to actually work really well. So I want to show you how that works here. This can also work in 3D, simplified 3D environment. So you have something, drone that's actually descending into an environment that is completely visually obliterated. Of course, it's using radio. The radio doesn't care about that, but for the optics of it, we show that. So here are two small radio tags. They're actually ultra-wideband radio tags that are on the ground. They're able to respond when the drone has a small tag on its own, and it's able to send out a chirp. The radio tags respond to the hello, and then that measures range quickly and uses that to localize the two tags and lands in between. So completely closed loop kind of thing. Now, the way it does this, what you see is a reconstruction. There are these two tags. As it flies around, as it gets there, and just in a few seconds, it's able to localize the two and then use that to get down. So this is some work done almost a decade ago that was then adapted into 3D to do this specifically for environments where there's no hope for doing anything visual. Okay, so I want to come to my third topic here, which is actually robustness to appearance and structure of the world, which is the topic that some of the speakers earlier on spoke about, which is, well, we all want to do SLAM, which we both want to know where the robot is and what's around it. But there's these two kinds of methods that are problematic if you are actually using IMU and visual odometry and LiDAR. They're problematic because, on the left side here, there's going to be very little optical texture. On the right side, there's very little shape variation. So it's very hard to match on either of these kinds of things. You can't really reliably track the visual side, and then on the right side, it's very hard to get any LiDAR, any differentiation from the LiDAR data. So the common solution we have is that combines IMU, visual odometry, and LiDAR. The question is, well, as is, it's a difficult problem to solve. Well, how are you going to do that? So there's two steps here I wanted to talk about. First is, how is it possible to actually even merge merge an IMU with the output of a visual odometry system? Well, so you could convince yourself that you have a good error distribution for visual odometry, and that can vary tremendously. Or how do you know what the error distribution from an ICP match is? So instead of trying to think about these all going into one big sort of a common filter, the idea is that we've set up a pipeline that starts at the IMU, and the IMU feeds the camera, which is some sort of feature tracking to help with the feature tracking. The feature tracking then helps with the LiDAR matching. And to give you an idea, the IMU runs at 200 hertz, the camera runs at 50 hertz, and LiDAR runs at something like 5 hertz. And these processes are then one feeds the other. So rather than having to combine them in some sort of common sense, what they do is they sort of like they set up the other problem, the next problem, which is lower in temporal resolution, to be able to produce then a map and a pose continuously. Okay, so this is the standard method. The assumption here is that in each of these, all axes that are computed with the same amount of goodness, so to speak. So that's a problem, and we could think about the fact that in reality, you don't have that. You actually do have this sort of problem of some cases where the state estimation is well constrained, and in some cases is degenerate. Now, there's a common sense way of thinking about it. If you have constraints from all directions, as you see on the top right, well, that's a well-constrained problem. If you have these constraints where in some axes you have almost no constraints, and other axes you do, well, then that's a degenerate problem. So the idea here is that if you can detect that, you don't have to throw out the baby with the bathwater. You don't have to throw out a whole mode. Although in the way that we've set it up here, it is possible if the camera were to, the lights were to go out completely, or the LiDAR were to stop working completely, it does resort to either a VO, IMU system, or an IMU plus LiDAR system. So it does do that, but you don't have to go to that extent. What you want is you want to be able to detect this degenerate direction, and then be able to use prediction from the IMU. And I think this Sebastian spoke about this also. This is sort of the same idea in the super odometry, I think, method that he mentioned. So you could do that. You can use prediction rather than the estimate, which could actually, if it's degenerate, could actually get you into trouble. And so here's an example of that, where you have this structural degeneracy and how it works. So we have this difficult kind of an environment where it starts off here. This is a LiDAR camera and IMU system. It starts and then it goes on this thing. But part of that is through a tunnel. And you see the tunnel over here. What happens is that if you don't do this kind of thing, the LiDAR starts to fail, and you just don't know it's failing. It looks like it's okay because you have good constraints from left to right, but in the forward direction, you just don't have enough constraints because the match can happen anywhere. It's very uncertain along the tunnel. So you get this kind of a thing. As soon as the vehicle comes out of the tunnel, it's able to recover, but what you get is something else. And if you properly, if you can discount the LiDAR, you know that there is a degeneracy in some directions. You stop believing it just on those directions, and then you can actually, in fact, recover the shape very precisely. Okay, here's my cheat sheet. it's a little hard to take in. Maybe it might be a good reference for later, but I go to this all the time. Part of doing robust perception is making sure you've got the right kind of thing, right kind of sensor here, and that seems obvious. But sometimes when you're really looking for different kinds of environments to work in, it's not that obvious as to what there is to do. But on the passive side, we have visible, which is just our visible EO cameras that we use every day, whether they're global shutter or not. We heard this great talk from Davide Scaramuza, who showed how to get extreme higher signal to noise, and of course that's always welcome. If you can do that in low light conditions or saturated conditions, but in fact, it's not going to help that much in rain, snow, haze, fog, and dust. These kinds of things, visible is not going to work. Now, if you have near infrared in rain and snow, you can do a little bit better. And if you have thermal imagery, you can actually do a little bit better in rain and snow, because you can actually pick up certain kinds of things in these kinds of conditions. As I showed you, when the visible imaging was being completely blotted out by the dust wave, the thermal imager was still able to pick up something. It's not able to pick up a whole lot, but it's still able to work here. Now, radio does work, okay? In radio, really, actually, I think, we call radio waves, we think of them in different ways. One is this ranging radio idea, which is if you have two radios, which you could use for localization, then of course you can use them in any kind of an environment. That works quite nicely, except for extremely, extremely wet environments. If you're underwater, radio is not going to work at all. Radar is a tricky thing to do because, of course, it's very tempting. It has the opportunity, has the possibility of working in all these weather conditions, but it turns out that metallic objects reflect much more than natural objects, and because it has a long wavelength, you have a lot of specular reflections off of grazing beams, so you don't get a return. If you're almost parallel to something, you're not going to pick it up because just the very little energy comes back. And of course, if you want a focus beam, then you need a very large antenna, or you need to do some sort of synthetic aperture method, which is you need to process data over some time to be able to then effectively create the effect of a much larger antenna. So these are, of course, the sensors that match. My last slide. What am I doing for time here? Okay, I'm doing okay for time here. Maybe this is.
You are. It's good.
Okay. All right, good. So for just as a last takeaway slide, mild obscurance, they'll diminish some range. If you have denser obscurance, they're either going to require multi-return ranging or classification returns due to the obscurance. Like I showed you, you can actually train something either from doing these local descriptors, shape descriptors that can identify the signature of vegetation or smoke or dust. You can do that through just simple eigenvalue kind of decomposition, or of course your favorite learning algorithm. You can do a supervised system, and you can then remove these kinds of these points due to that. Radio works, like I said, in most cases. It's actually quite amazing, except of course it's not going to work when it's very wet. If you guys have a automatic cruise control radar on your car, you might notice that if you're in a very, very heavy thunderstorm, your radar will stop working. It's just because radio doesn't do well with water. It's much better as a heuristic on localization than an obstacle detection, simply because any reasonable radar antenna is going to produce a very wide beam, and of course then you have this other problem of things reflect very differently based on whether they're metallic or not. And you, in addition, have something called side lobes, which sort of like find things on the sides and can be confusing. So the last 2 points have to do with how you merge the data and whether, where the degeneracies are. It's hard to merge this data from, IMU GPS. We know how to do that. We can think about the uncertainties due to that, but it's really hard actually to get a good error distribution on even a simple range measurement from a LiDAR, let alone something from an ICP-like system that actually does a match. So you're trying to match these two things and try to understand them. So the way we've had some been able to do get some good results is that we use one method to set up the other method and so on to be able to do that. We call those stacked estimates. This is work due to Ji Zhang, who's actually changed quite a bit of how we think about merging these three estimates. And then the last part here is degeneracies you have these degeneracies just due to the appearance and the shape of the natural world. And they require some sort of selective use of sensor data, which is not just, should I use this modality or not, but which direction am I going to use? Or I can select even between the estimate here. In some directions, I'm going to be okay to be able to do that. And we have a simple heuristic to be able to figure that out. So I'm going to stop there. Thanks for the invitation to speak here.
Perfect. Thank you very much, Sanjeev. Fantastic talk with a lot of amazing insights. Thank you for sharing all that. Just again, as a reminder to everybody, please do add your questions to the Q&A. So we'll be taking those questions during the panel discussion in 20 minutes from now. And with that, it's my great pleasure to introduce our next speaker, Professor Barfoot from University of Toronto, Canada. And he will be talking about robotic localization challenging environments in dark, damp, and dynamic settings. And Tim, please take it away. And we were able
sorry,
to...
I couldn't find the unmute. I had to make the screen small again. One sec. How does that look?
Yes, I can see it now. Perfect. Yeah, thanks.
Okay, great. Well, thanks very much to the organizers for the invitation to give this talk. I'm going to leave it as a bit of a quiz. What do you think the video in the top left is showing? If you think you know the answer, type it into the chat window and we'll score you at the end. Okay, so I thought today I would just actually give a little bit of an overview talk on some of the different activities that are happening in our lab. I'm going to give a bit of an update on our long-term effort on multi-season visual localization. I'll then jump into how we've been looking at GPS as a tool that could augment vision in a couple of different ways to help sort of cover off some edge and corner cases in our navigation framework. I'll talk about how we've been getting visual teach and repeat up into the air and some of the challenges around that. And in particular, we've been thinking about how to localize against satellite images or images that we get from Google Earth and some of the domain transfer problems that come along with that. I'll then switch gears a little bit and start thinking about how can we start to leverage some of the recent successes in deep learning in order to be able to learn features for these pipelines that we've been using. And I'll talk about how we've been doing that for both LiDAR and radar. And then finally, I'll close out with a fairly different kind of project where we've been looking at using LiDAR and a learning method to try to classify at the point level, point clouds, LiDAR point clouds, so that we can try to sort of filter out different types of objects and their permanence in the scene to try to help with different blocks in our navigation pipeline. So let's jump in and do a little recap on this technique called visual teach and repeat. So for many years, my lab has been working on this visual navigation framework called visual teach and repeat, which basically is a framework that lets a robot navigate through an environment using only vision, and it can be an unstructured environment. And basically it works in two phases, a teach phase where you go into a new environment and you give a training example of every path segment that you'd like the robot to operate on. And these can be all interconnected paths into a whole graph of different paths. And once you've showed the robot those different paths and it's been able to build a map using its camera, you go into the repeat phase where you drive automatically And we see here the robot driving automatically on one of these paths. So it's just matching its vision data back to the map that it's stored. So it's a pretty efficient technique. Just uses one laptop, one camera, one training example of every path. And it's pretty lightweight in that it doesn't require GPS in its nominal setup. It doesn't require IMU. We don't tend to use DNNs, although we'll talk about that a bit today. No global map and no semantics or requirement for structure. And then one nice property that it has is that it's composable, which means that we can actually string together the different training experiences or segments into previously undriven combinations of paths so that we can basically operate anywhere on this graph and drive where we want. And we've been working on this for a long time. And I guess my lesson learned from all of this is that there's sort of two key ingredients that make visual teach and repeat really effective. The first is the fact that we use a relative map structure. And so when we're teaching the path, we actually just perform visual odometry and we don't try to make the map make sense in any particular global coordinate frame. We just estimate relative motion and then we store the landmarks that we've seen relative to the poses from which they were first seen. And so that's actually a pretty lightweight thing to do. You can actually build the map on the fly and you don't have to do any big computation at the end in order to make it make sense in a global reference frame. And then when we come to localize, we can actually just rubber band a small section of this relative map structure, identify common landmarks to our live frame, and then work out the offset between the current pose and the map. And we can run visual odometry in parallel with that, such that if we don't match, we can still continue. And then hopefully we can find some common landmarks to our map again, localize, and then figure out this offset. And once we know the offset from the path, it's a small matter of using something like model predictive control to look ahead at the shape of the path and figure out how to zero our errors over the next few seconds. The second key ingredient that's made visual teach and repeat successful over the years is our ability to handle large visual change. And you might think, well, cameras are not very good at actually handling massive changes, but we have a special opportunity, I guess, in path repeating, in that every time we drive a new path, or sorry, redrive a path that we've been on before, we get a new experience of that path and we can store that. And so we've built up a technique called multi-experience localization that effectively continues to take the original path and that visual experience and augment that with all of the subsequent drives, so that when we go to localize, we can actually use all of that information to figure out where we are. So we could teach a path in broad daylight, chain it through the lighting, changing into the nighttime, and then be able to match nighttime back to daytime. Even though those don't match directly, we can go through the intermediate experiences. And this builds on a lot of previous work that came out of Oxford and their experience-based navigation framework. So putting all that together, we've kind of tested this visual teach and repeat system on a number of different robots over the years, targeting different types of applications, everything from underground mining to planetary exploration and unmanned aerial vehicles. So I can refer you back to some of the previous papers if you're interested in learning more. So that comes to sort of the more recent work that we're going to present this year. So actually just last week, my student Ben Congram at the Canadian Robotics Conference presented this paper called Relatively Lazy, Indoor-Outdoor Navigation Using Vision and GNSS. So we've been thinking about some of the edge and corner cases for visual teach and repeat. Of course, if you were paying attention to what I just talked about, we can basically match things across large lighting and weather change, but we have to do that incrementally. And so if we allow sort of a big temporal gap such that the appearance changes too much from teach to repeat, we're kind of dead in the water. And so we've been thinking about using GPS kind of like training wheels. So maybe for a while, when we're in a new environment, we could actually use GPS. And if we're not able to match visually, we could use it to lay down a new visual experience. Once we have enough visual experiences to sort of span the ways that the world can look, we could take the training wheels off and then we wouldn't need GPS anymore. And so this sort of leads to this indoor-outdoor kind of framework. Vision tends to work well inside where lighting is consistent. GPS only works outside where you have a clear view of the sky. And the question is like, can we put these together in a meaningful way? Many people have done vision and GPS before. I guess the challenge for us was how could we do it without sort of giving up on this relative map structure that we'd previously established in the visual teach and repeat framework. And we kind of do that. I guess the title of Ben's paper kind of explains the whole thing. We do that by being lazy. So We actually don't do sensor fusion between the vision and the GPS until the last possible moment, which is basically when a path error is required by the controller. And so the idea is, we essentially compute a path error with GPS alone, with vision alone, and then loosely couple those and just fuse them at the last moment. And then we can be opportunistic about which sensor is available in order to sort of be robust to both not having GPS and not having vision in different parts of the path. So here you're seeing an example where we're transitioning from indoors to outdoors. And of course, there's a challenge around that handoff between the vision and the GPS, which happens sort of natively through this relative framework. Another really counterintuitive thing that we're doing with GPS is to use it as an odometry sensor. So in the previous slide, the GPS that I was using was an RTK GPS that required a base station. We asked ourselves, what can we do with just a single low-grade GPS sensor? And it turns out that you can actually do something pretty interesting. You can build a fairly high precision odometry system just using a single low-grade GPS sensor. And it works basically by using these time differenced phase-based measurements and techniques. So as a satellite moves to the sky, you can sort of measure your change in the phase of the range measurement to that satellite. And that tells you something about the motion between these two robot poses. So if you think about it that way, you can think of the robot acting as its own GPS base station. And I put this albatross here to remind me to say that this technique is actually not new. People have been using this in other domains, such as biology, to track the motion of birds, for example, and albatrosses particularly. So once you do that, and you can sort of build up a factor that tells you something about the motion between these two robot poses, you can pick your favorite paradigm and incorporate that information into your estimator. And I guess the bottom line of this is, here's an example of some quantitative results over a 50-meter distance, showing sort of the drift of visual odometry in this really dirt simple GPS odometry. And in our experiments, we found that the GPS odometry had about a quarter of the drift rate of visual odometry. So you can imagine a situation, perhaps the robot's driving, some mud splashes up onto its camera. It would be nice if we could continue to drive, and perhaps we could use something like GPS odometry to do that without any special infrastructure other than the satellite network. So now moving to talking about getting up into the sky with unmanned aerial vehicles. A couple of ICRAs ago, we gave a first paper on putting visual teach and repeat up onto UAVs, and we were using that as an emergency return function, or we were motivated by that problem. So you could have an outbound flight using GPS, and then if GPS or comms were to fail, you could sort of rely on this map that you built on the outbound pass to fly back to the starting location and land. We showed that we could do that, but we were challenged a lot with lighting change, and sort of the point features that we were using on the ground didn't work nearly as well in the air. So last ICRA, Bhavat Patel, who's Angela Scholig's student, and I joined for this paper. They looked at using mutual information instead of point features to do the matching. Unfortunately, that worked well, but unfortunately it was a little bit slow for us to implement it in real time. So this year at ICRA, my student Molly Bianchi is presenting a paper where we use deep learning for this problem. So we actually train an autoencoder to effectively, we push the satellite images through an encoder-decoder network, and you can kind of see the reconstructed images over here. And then what we do is we take this bottleneck vector, which is pretty low dimensional. We run the same encoder on the live images from the UAV, and then we can directly compare these bottleneck vectors. And we're actually pretty brute force about this. We render these bottleneck vectors from the images from the satellite images on an array. And then we take the live image, encode it, and we compare that live image vector to every image that we've got stored in this array, which sounds like it would be very expensive, but it's actually easy to parallelize on a GPU. And so you can get real-time performance with this. And so here's an example of actually us localizing a live UAV image against these images that this map that we built just from the satellite images from Google Earth. And if I zoom in on that, you can kind of see there's a heat map. The yellow color is showing that we're more likely to match, and sort of the purple dot is the ground truth. The red is our best estimate of where we are. And this is without even filtering it. This is just processing one image at a time. And I forgot to mention that one thing that was really good about this is that we effectively successfully solved the domain transfer problem. And what I mean by that is that we trained this network using only the satellite images. And yet we were still able to take that representation that was learned by the bottleneck vector and use that same encoder on the real images in order to do the comparisons. And that seems to have worked pretty well. So if you're interested in more details there, you can check out Molly's talk, which is tomorrow. Okay, so changing gears a little bit, I'm going to talk about learning features now. And in particular, we've been thinking about, like, we've been using these handcrafted features in these pipelines for quite a long time. There must be some benefit we can derive from deep learning. And so we started scratching our heads about what's the best way to do that. Of course, we could think about, handcrafting everything, which is what we've typically done in my group up until fairly recently. Or we could think about sort of taking the more extreme position of let's deep learn an entire navigation pipeline, which didn't seem like it made sense to us. And we've kind of landed somewhere in the middle where we're thinking about learning features from some kind of rich sensing stream in the front end, but then combining that with a classic backend to retain all of the advantages of that. And so we think this is sort of the getting the best of both worlds combination. We're able to sort of do this complicated unraveling of rich sensor data that deep learning is good at, and yet we can exploit things like robust estimation, ransack, in order to be able to deal with out of distribution data. And so we've been learning features and then using classic backends. And in particular, we're training this end to end. So what I mean by that is it's not an end-to-end learned pipeline, but we're training the learned features in concert with the backend, classic backend. We do this without any ground truth, so it's completely unsupervised. And we do it without the backend being differentiable. So I'll talk a little bit more in detail how we do that. We're building on some work that came out over 20 years ago in this paper that we quite like by Zubin Garamani and Sam Rovice, where they combined RTS smoothers with radial basis function networks 20 years ago. So we basically modernized this idea. And what we do is we start from a single learning objective, which is, let's imagine notionally that we're thinking about a LiDAR odometry pipeline. What we like to do is maximize the likelihood of observing a LiDAR sequence given some network weights. And to do this, we introduce the latent state, which is the robot trajectory. And we do the classic decomposition of that learning objective into the KL divergence and what's called the negative expectation lower bound, which we'll just call V. So EM works by effectively ratcheting down this expectation lower bound in two steps, expectation and maximization. So in expectation, we hold the network weights fixed, and we try to minimize V with respect to the robot's latent trajectory, actually the distribution over it. And in the M step, we hold the robot trajectory distribution fixed, and we try to improve the network weights. And we can do that using standard backpropagation. And we do this completely unsupervised. So graphically, I'll say it one more time with this slide. So imagine we've got a sequence of LiDAR scans. We want to estimate this trajectory. In the E step, we just actually forward propagate the LiDAR scans through our deep neural network. In this case, for LiDAR odometry, we're using 3D convolutional layers in the form of something called KP-conv into some fully connected layers. And we get the network to output not just features, but also descriptors for those features and covariances for the features. So they try to represent their own uncertainties. We then do a differentiable matching step where we are able to pair features from one LiDAR scan to another. And we put those into a factor graph. So we can see these black dots here. Finally, we can incorporate, because we're using this classic backend, we can incorporate other factors into the same factor graph. They could be motion models, could be IMU data, could be anything that you like. And then we run this to convergence to come up with a distribution for the robot trajectory. So that's your classic trajectory estimator. If we were just doing estimation online, we would stop here and we might slide this window forward in order to do odometry. But if we're training, so we're still trying to learn the network weights, we also have to run the M step. And in the M step, we hold the robot trajectory distribution fixed, and then we just backpropagate through all of these differentiable functions using standard deep learning tools. And again, I'll just stress, we do this completely without any ground truth, just from the sequence of LiDAR scans. Here's a couple of videos showing how this works. So I'll draw your attention to the left side where we're doing training. So we start with random network weights, and by successively applying the expectation and maximization steps, eventually over time, we see that the robot is able to figure out some internal representation of these features that's very good at estimating motion. And I guess it's the geometry of the trajectory estimator that's forcing it to do that. And at the end, we see that it looks much closer to ground truth. On the right, we see testing. So here, actually, this is some kitty data. We can see the estimated trajectory qualitatively. And you can also see all these features and those covariances that are being used to estimate that motion that are coming out of the deep learning algorithm. If you're interested in more details on that, you can check out this paper that'll be presented by David Yoon tomorrow, which is also nominated for the Best Student Paper Award. We've been doing a similar thing on radar, motivated by the ability to try to do radar odometry in serious, difficult weather. Similar, I guess, to what Sanjeev was talking about. Here's some data from just outside our lab in Toronto this past winter. It doesn't look like sunny California, where most self-driving research is being done. And we're able to apply that same pipeline in order to learn interesting features for this NavTech radar that we see over here on this car on the bottom left. And this is a depiction here of some of the features that we're learning from that radar stream. And if you're interested in that, you can check out an upcoming paper at RSS 2021, where we're learning radar odometry features unsupervised. Even before that, though, we've also been doing some work on radar just to think about how to even deal with the motion compensation issue. So this radar that we're working with has, it's a mechanically actuated spinning radar. So we actually have to deal with the motion compensation issue, because if it only spins at 4 Hertz and we're translating at 20 meters per second, we get a significant distortion. And so one of the advantages of using this, this sort of classic backend learned front end is that we can incorporate things like motion compensation that we already know how to solve into the backend problem. And there's a paper by my student Keenan Burnett, co-supervised with Angela Scholig here at ICRA, talking about motion compensation for radar odometry. And I'll just finally turn to the last project we've been working on, which is a little bit different. It's focused on an indoor navigation problem. On the left, you see a scenario that many of you may be familiar with. If you've ever given a robot demo in a crowded space, all the spectators want to come and see what you're up to and what your cool work is about, and they come and they stand around your robot, and then the robot gets really confused and it can't solve the problem. So we actually devised this adversarial simulation where we had these weird automaton human things trying to crowd the robot and make it hard for it to navigate through the space. And so our idea was, could we actually get better at using semantics to solve this problem? If we could classify things as humans, furniture, permanent structure, it would be a lot easier to solve this problem by filtering on those different classes. And so we have this vision of lifelong learning for an indoor robot. And the idea is kind of like this. We first might take the robot into an environment and sort of let it build a map by driving it around a couple of times with people and furniture and all different things in the scene. And then offline, we could leverage the fact that we already know how to do sort of multi-session SLAM in order to label all of the different things in the scene automatically using the SLAM algorithm as permanent structure, furniture, and dynamic objects. And so we can do that. It takes a long time, but we can crunch that offline. We then use those labels to train a neural network in order to make those same classifications online in real time. And so we've been able to do that. And so once the robot has that network, it can then use those classifications online to do a better job of navigating, go out into the world, get some more data, and then come back and sort of process that the next time. And we'll just continue in this cycle in order to let the robot get better and better at classifying different things in its environment over time. And so there's a paper by my postdoc, Hugh Thomas, who's speaking about that on Thursday here at ICRA. Here's just a preview of the classifications that we can get out of this 3D network. So we're actually labeling every point in the LiDAR point cloud based on one of these 3 classes of short-term movable, long-term movable, or permanent structure. And so I guess a nice property of this is that we're basically not having to have humans draw boxes around other humans in data in order to be able to make these classifications. It's sort of self-supervised just from the basic properties of SLAM that we can do offline. And just as an example of what that buys you, if you filter and you just say for localization, you want to filter out all the dynamic objects and the furniture and just localize against the permanent structure that's in your map, you can do a little bit better in sort of crowded environments than sort of just using all the points together. So we can see here that we've improved our localization performance, our errors. But there's other things you could do with this as well. Okay, so I'm just going to wrap up with some lessons learned. I think long-term localization is still not easy for all environments all the time. I wish it were. You know, Larry gave us an even harder problem to work on, which is landing on Titan. Lots of challenges still remain for, I think, lifelong map updating in particular for dark, damp, and dynamic scenes. I think we're still not great at building and maintaining maps over the lifetime of robots. Certainly, we've seen this theme come up in this workshop. Complementary sensors can help. Machine learning, I think, can also help. And I would say more broadly, data-driven methods, right? I'm thinking in terms of our multi-experience localization. That's a data-driven method, although you might not call it machine learning. I also like this idea of classic methods offline as supervisors for training neural networks to do the same job online, but faster. I think, you know, having to label a lot of data sets by hand seems like not a great sustainable prospect for robotics. So if we can self-supervise to train machine learned models, that would actually be a useful thing. And then I guess maybe a holy grail problem is how do we automatically learn good long-term map representations from data? I don't know how to do that. If someone does, I'm eager to know. I don't think benchmarks are a great source of long tail events for really stress testing our localization algorithms. Once a benchmark is out there, we get very good at solving that benchmark, and then there's plenty of other ways that our algorithms can still fail, and yet we sort of put the blinders on and focus on the benchmark. And then I guess a question maybe for the panel session is, are we even prepared for or suited to studying long-term localization in academia, just given sort of the scale of the experiments and the difficulty of sort of these long tail events? Can we even do it? So I'll stop there. Thanks very much to all the sponsors who have supported these projects over the years. And I'll just leave it on this slide, which just advertises our upcoming ICRA talks at this ICRA. So thanks very much for your attention, and looking forward to the panel discussion.
Thank you so much, Professor Barfoot. I'm taking over from Ali. I'm Andrew Kramer, one of Chris Ekman's students. Like to go straight into the panel, but before I do, I think the question on everybody's mind is what was the source of noise in that image on the first slide of your talk? We had guesses from.
I couldn't see the chat. What were the guesses?
We had guesses from sensor noise to snow to bugs to blowing leaves.
It was bugs.
Yeah,
it was bugs.
Okay, plus
lots and lots of mosquitoes.
Plus 1 point for everyone who said bugs or mosquitoes.
And the great thing is, just in case anyone wanted to know this, the surf detector fires on mosquitoes. So it will work. I know you wanted to know that.
Now I know how to train my little pan tilt turret for mosquito hunting.
Yeah, that was not a fun experiment to do, by the way.
Where was it?
Canada.
Oh, okay.
All right.
Okay, I'm going straight into some of the questions we've had, and actually, as a reminder to all of our participants, you can add more questions in the Q&A box as they occur to you. But I'll ask one of the questions. Let's see, one of the questions that we had for Sanjeev. You talked about, you did several experiments and talked about challenges using LiDAR and vision in using thick obscurance like very heavy smoke or the dust kicked up by that Black Hawk helicopter. Have you done any experiments using radar, or just the experiments you discussed with ultra wideband? And do you have any thoughts in particular on radar that you didn't mention in your talk?
Yeah, actually we did. I didn't show some radar data that we took at that exact spot because it's a little harder to correlate. So in that big sensor suite that we had at that place there, we had a 6 gigahertz radar. The problem with radar, as I mentioned in my talk, is that generally you get a pretty broad beam. Okay, now if you have a radar on your car, it looks like, okay, it's a pretty small sensor here. It's because you can do some processing and assume that what you're seeing on the road is another car. And you can pick up on these kinds of things and localize on those kinds of things. So what you're seeing is mostly cars. Just a hint to anybody who's thinking about doing this, because I have one of these things that I try to play chicken with my car sometimes, is try to see what kind of things it can detect and not, is do not hope that your radar is going to slow you down when you come to the toll booth, okay? It turns out that it's actually pretty bad at detecting those kinds of things, especially if there's no car there. It's at the toll booth. So if you're going to a toll booth and there's no car there, it will not slow down. Sometimes, okay, it will not detect that kind of thing. So I think one of the problems with radar is just the difference in reflectivity from metallic objects and non-metallic objects, and the sort of specular reflection that you get. So it's a long wavelength compared to light, and basically, unless you're pretty much at 90 degrees, you don't get a reflection from the surface. So that's a problem we have with radar. Now, there's all kinds of different radar methodologies that people are using, including doing a little bit of post-processing, doing some batch to get the synthetic aperture method. Some of them are actually trying to do some scanning to be able to achieve some of that same effect. I think that they are approximating, they're trying to find a way to focus the beam over some time. So radar is actually quite promising if we could somehow or the other find a way to get returns from all the things that would fool you, right? For aircraft, one of the things we look for is wires. And radar is actually pretty bad at detecting wires reliably. Sometimes you get a fantastic return, and other times if the wire has not got any metallic thing in there, you'll get absolutely no return. Same with vegetation. Sometimes you will get something from vegetation. Of course, you know, you're looking at a big tall tree. If you're flying at 50 feet or 100 feet, you're going to collide into that. Radar might not even see it. So we have these kinds of problems because radar is not really actually designed for that kind of thing, that some of which can be mitigated. One of the things we've been looking at is using radar to land safely in a complete whiteout without any kind of cooperative infrastructure on the ground. And then you can do some sort of synthetic aperture through dense fog or smoke or anything else like that, and actually can figure out, can reconstruct the three-dimensional environment before you land.
I mean, just personally be very interested to hear more about that synthetic aperture landing work, but yeah, I'll check your website for that.
I think there was I think there's a question for Tim that just came up. If we could ask that. Tim, you can probably read this in the Q&A, but it's for using classical methods for providing ground truth and unsupervised learning when you're training based on some classical type of technique, does it mean that the performance of the learned model is limited to how the classical method works? And I think, you know, you can pick this answer however you like, but I think this is an interesting question because we see some of this, Sanjiv, the reason why Andrew's interested in that radar work is because we do LiDAR radar transfer learning stuff. So maybe Tim, what do you think about that question?
I mean, yeah, clearly the performance is going to depend on how good the classic labeler is, so to speak. You know, it probably varies from case to case, but in the examples that I showed, the feature learning stuff, you know, we're using a Gaussian representation of the trajectory, which is common in robotics. It's going to be limited by that assumption, right? So if you have a multimodal kind of hypothesis that you need to represent and you pick a Gaussian, it's not going to be very good at that. In the indoor navigation work, I guess we sort of picked a learning problem that was well matched to what our labeler could do, right? So we weren't trying to put bounding boxes around humans or do clustering. it's actually pretty easy to detect if a point is in common between two LiDAR scans, right? And so you can do that either temporally within one sequence of LiDAR data or across sessions in order to get these labels of short-term movable, long-term movable objects. That's a fairly robust classification that can be done, but it requires the benefit of sort of acausal knowledge to do it really well, which means you can do it offline, then train the network from those labels that are pretty good to do those same classifications online. So I guess it does depend, but you can also be smart and not pick a learning problem that exceeds the capabilities of your labeler.
That's very interesting.
And I'm going to answer the other question too, which is, if you want to know more about radar, there was a whole workshop on radar this morning, the radar and robotics workshop that I attended. And I think they'll probably put all those talks up. So for those interested in learning more about radar, there's probably like 5 hours of information there that you can chew on.
And I see Sen Wang in the audience here, so I'm guessing those will be uploaded. There was a follow-up question I wanted to ask Tim, which was that you said that you sort of are using data-driven techniques for the features, but still using like the standard techniques for like creating cost functions and optimizing them, for instance. And I'm curious what you think about the works that are like dabbling, GNNet or other types of works that are sort of dabbling in the area where they're constructing cost functions based on data-driven techniques, or even replacing the optimizer in some cases. And I guess you're picking your line in the sand. That's totally reasonable, but I'm curious.
I tried to be very diplomatic about it by saying there was a whole spectrum and a whole bunch of different things you could try. The thing that we're trying is sort of, I'm a state estimation person, so I like these classic state estimation techniques. I don't really want to try to train a neural network to learn about matrix Lie groups. I already know about those, and I can probably write down the math of those. So, why learn something that you already have a very good model for?
Yeah, that's fair. I was just curious about, the line in the sand is drawn regardless, but I see what you mean is that the feature side being data driven is, it's just a swap for a hand engineered feature.
It also comes down to what you're trying to do. If you're trying to build a really good system to work in one environment, maybe you don't need learning at all. I think the benefit of learning is that it holds the promise of being able to generalize across different environments, right? So I think that's sort of my interest in it. I think, the same front end could be used to learn features for LiDAR and radar. That's interesting to me. If I just want to build the world's best, well, Sanjeev already built the world's best LiDAR odometry, and it's held that spot on the Kitty leaderboard for years. So like, I give up trying to beat Loam. What I find interesting about what we're trying to do is that the same algorithm could be used, for different sensors in different environments. And I'm interested in that question of generalizability.
So
sorry, go on, Sanju.
Go ahead.
Can I ask a question? The thing I was curious, because I don't work in this area that much, Tim, I'm not familiar. I'm going to go look up things, but for others also. What are these features that are being learned, right? Self-supervised, and why do you think they would generalize across, or you think the method would generalize across?
No, the method is the thing that generalizes. So like if you want to learn features in this environment, so we did an experiment in one of the papers where we sort of trained features on the Kitty data set and then tried deploying those features, say on the Oxford data set, versus training on other data from Oxford and deploying in Oxford. And we showed that we could actually sort of fine tune the features for a particular environment by training in that environment. So maybe there's some benefit there. Honestly, I'm not like evangelizing deep learning. We're experimenting with it to see what the benefits might be.
But just let me push it just a little bit more, because I'm curious, what is your insight? What do you think are these features? Are they some version of corner features that are sort of easily distinguishable? Is that what's happening? I see these things, there were nice, interesting looking ellipses associated with them. Is that what's happening in these different kinds of data sets?
It is, but it is. So we're specifically trying to learn point features, but on the other hand, it wouldn't have to be point features. You could get it to learn other types of features, but we're also doing this at multiple scales. So, there's this sort of like autoencoder bottleneck kind of architecture in the network. And so we pull the descriptors out at different levels within that bottlenecking process. So it's a little bit more like I guess a surf feature, right? That's a multi-scale detector. We can find it at different scales in the image. So it isn't necessarily all little corners of one size. You might find, at some other level in the image pyramid, you might find something interesting to pay attention to as well. So I guess the features are somewhat interpretable, but somewhat not interpretable, I guess is my hedging answer to that.
Yeah, that's the trouble, right?
Yeah,
I get it.
I agree.
It's attractive because but
I'm not trying to sell you on deep learning. I'm trying to say, what could we do with deep learning in order to benefit state estimation? And this is one possibility.
Cool. I'd like to bring up another question from one of the participants, and that's what's your take on doing sensor fusion or state estimation in visually degraded environments that are already very feature poor, whether you're using LiDAR or like that's a flat environment for LiDAR, or with vision if it's just very low contrast. Do you have insight on that?
I'm gonna take it. Yeah, I'm gonna take it a step further, and I'm gonna say, what if it's varied, and we've already followed Sanjeev's advice on putting the right sensors on. Okay, so we have the sensors on the platform, and the environment is varied. We're going out into an environment, but we have every sensor we need. Then what?
So let me take that at some level here, and then he'll add his words of wisdom here. The idea, I think, is that we realize quickly is that, okay, not only do you have the right sensors, okay, that's like common sense, right? But what is that common sense? I thought I'd put it in a slide there. But beyond that, one is when does a sensor fail? When are you not getting information in it? And what you don't want to inject into your system is noise from a thing that, hey, just because we have complementary systems, these things are going to do the right thing. Partly because it's not easy to always come up with goodness of any kind of measurement. One of the things I have questioned, maybe Tim will answer me another time later, or he'll choose to answer, is like, when you're using GPS for ground truth, how do you deal with the fact that GPS sometimes will lie to you? Which is, it will tell you it's extremely confident when it's completely wrong, okay? And it could do that for various reasons. Satellites being, out of the ephemeris, or you get a multipath or something else like that. We often have this case where GPS is extremely confident, but it's completely wrong. And so that is a kind of a problem here, is that it's hard to get goodness of a particular mode here, if you think about these sort of like, loosely coupled kinds of integration. But the notion that you can actually test for where the constraints are, okay, that I think is okay. That says, all right, in some dimensions, you might be able to, even within a mode, you might get some information, but just don't throw the whole mode out, or just take it for granted, because you should just be able to pick out just the kind of the axis in which that mode is giving you information about. And so that would be another one. Now, this thing sort of goes to hell when you have a really bad environment and you may be getting nothing in that case. And then you do what Sebastian said earlier, which is essentially use proprioception. Some form of proprioception is what you try to, that's how we deal with it. If you are faced with a completely dark environment, all you know is how your body is moving, and you can sort of like test it. Now it's going to be really bad, but that's all you're going to be able to do. Tim, you have something deeper than that? That seems pretty obvious to me.
No, not really. I mean, I don't know. The question is a difficult one. It's like, what combination of sensors should I use to work everywhere? I don't know the answer to that. I mean, that sounds like a hard problem, but I could answer Sanjeev's question, which is about GPS. I kind of agree. I just think of GPS as another sensor now. I've stopped thinking about it as a source of of truth in some ways, because it does lie to you. You have to be careful about satellite handoffs, multipath reflections. Don't trust the dilution of precision, that's for sure. I don't know. In many ways, we often submit these visual path following papers and people say, well, where's your ground truth? And it's like, you know what? Our vision system is doing better than the ground truth now. And we can prove that by like marking points on the ground and proving that we can actually know where we are better than the GPS knows where we are. So it's, it's another sensor. Use it like another sensor.
So I really do appreciate that, Tim, and I love that about your work. So thanks for sharing that with us. And what I want to say too is that I found this question to be still fascinating because, like, again, it's not a question of which sensor should I put on my robot. Let's say that we followed Sanjiv's advice, but I think that there are other systems that have to sort of do the fault detection that Sanjiv was mentioning, and then, adapt somehow. And maybe in the end is proprioception. And Jeanette made some comments to that earlier during her talk too. So for slightly different problems. Did you have another question queued up, Andrew? And we've already gone over time, but the talks were slightly, scheduled disjointedly. So maybe we will, if you don't mind, we'll maybe take 2 more questions and then we'll give some closing remarks.
Sure. I have another question that came in from one of the participants. I think they give the disclaimer that it's more of a technical question, but they're wondering how stable the expectation maximization approach is for learning sensor features and estimating trajectory simultaneously, and if any outlier rejection is employed. They give the example of the effect that an incorrect loop closure in odometry or SLAM can have on the overall estimate.
Yeah, I can answer that. So EM it's not a global optimizer, right? So it's going to find a local optimum to your data likelihood objective. So that's one thing, right? So it does require a reasonable initialization. On the other hand, we found that initializing to random network weights still does something useful. How stable is it? Stable is a very particular word which would imply some kind of repeatability, right? So if I run the same data through it, do I get exactly the same thing every time? The answer to that is no, because inherently, even the deep learning training has an element of randomness in it, right? So if you're employing stochastic gradient descent, which is the big hammer in deep learning, as the M step, then you're going to get a different answer every time you run. But we don't get wildly different answers. We get things that look pretty similar from one trial to the next, even starting from the same data. I forget the other part of the question, loop closure. Oh, outlier rejection. We do imply outlier rejection both in training and in testing. So the testing was sort of like my pitch for why the classic backend is actually a good thing, because it can police the deep learned front end. Even if it makes mistakes on out of distribution data, we can still handle that on the back end. But we also use outlier rejection in the training, and that's actually quite important. So if the deep learning tool is saying to match things that shouldn't match, we don't want to reinforce that. Just because it also matched some other features that provided a good estimate, we don't want to say, well, reinforce this bad estimate that just happened to be in the mix, this bad sort of association that happened to be in the mix with the good associations. And so we actually don't back propagate on outliers. And that was sort of key to making that work. We don't do loop closures, so I don't have a comment on that.
I think I've synthesized a final question for the panel for both of you, and it goes out to something you mentioned, Tim, which was that, should we be doing research in long-term autonomy as members of the academic research community? And I think it was based in because, it's extraordinarily expensive to run platforms for a long time. There was an earlier mention about data sets during a previous panel, data sets being sort of like the purview almost of like a different community. Like we're a robotics community, we should be testing things, and we can't, what robustness means doing better than just doing well on Kitty or UROC or TUM or something. And so I'm curious, if you have any thoughts that you can share with us on that, Tim, and Sanjeev clearly being the CEO of a company who's working in some autonomy, I mean, you know, was that a factor in that decision making, or is that just, you know, is the kind of work that you're looking at sort of transparent to that boundary between the two different areas that you do the work? So Tim, maybe you could start.
Sure. So I guess I posed that question just because I do find it a bit of a challenge to work on these long-term, I didn't say long-term autonomy, but you could generalize what I said to long-term autonomy problems.
Yeah, right.
You know, it just takes longer and longer to run a reasonable experiment in order to prepare a paper to say, I did better than the thing that already is out there, right? And so how do you do that? I don't have a good answer, but I would say robotics is in an interesting place right now, in that companies have taken an interest in robotics and are sort of trying to roll out real world applications, and they can actually throw their weight behind these applications a lot more than we can in academia. And you can see now, you know, companies putting out these big data sets like Waymo and Autonomy, et cetera. That's great. I'm super excited to see that they're doing that for the community. We should make use of those data sets. But on the other hand, I also think data sets don't quite cut it, because you get very good at the benchmark, right? And so I guess in my own research, I want to try to do both. I'm going to use the data sets that are coming out of industry, which are also, you know, better than the ones that I can possibly gather most of the time. And then I guess I'm also going to want to keep using my own robots, because I feel like I'm going to find some edge and corner cases that just aren't in the data set by sort of getting the experience myself. So that's sort of been what we've been doing. Some experiments with our own robot, also quantitatively run on data sets from other people. But I don't have like a great solution other than that. Maybe Sanjeev has the answer.
So Tim, you asked a great question, and I think you gave a good answer to your own question. I think in my view, you know, robotics has come a long way, but if we want to continue to make progress in here, then the next step, whether you're doing it from an academic perspective or from a commercial perspective, we have to be able to do this kind of long-term kind of thing. It's actually an interesting puzzle for me, right? I mean, from just a completely academic setting or point of view is like, is there an invariant if you're flying an aircraft, say 100 foot above the ground or up to 500 feet up above the ground, that I'd be able to localize on some visual features, summer, winter, fall, on a rainy day, on a sunny day. So what is that invariant? I think that's not completely obvious, that there is an invariant of what the features should be, or how would we find them, et cetera. So this is, I mean, you know, it's a question worth asking, because we have sort of exceeded the bounds of we can do things in indoor environments or built environments. And from a field robotics perspective, I think this is the question actually. Can your system work in all kinds of things? I'd settle for doing something in an environment without actually having to tune the weights all the time. One system that works 365 days a year. Okay, not in the worst blizzard and not in the worst rainstorm, not in the middle of the night necessarily, but in, you know, generally where you would expect the vehicle to work. I'd expect it to not have to go out and tune it for that kind of system. So I think we need to do that. Now, the greater puzzle, I think, is, well, if you could train it here, will it work over there? So if probably if I train something in Pittsburgh, it'll work in Toronto. But if I train something in Pittsburgh, will it work in Phoenix? Or, you know, not train in the classical sense of train. It's just like if I develop a system that can localize or it can detect objects, will it work in a different setting? That's not too exotic or anything else like that. So I think that's a harder problem, because it gets to what is really actually a much larger of the general problem of AI. But I think the first one, which is taking a practical with and having it work across the year, all the kinds of environmental in a year, I think that's a very to ask. And reasonable, but I think it's actually a essential question to address.
Thank you both. Really appreciate your time and your presentations. And thank you for your insights at the end. That's very helpful for us. So now that this panel's concluded, Andrew has some closing remarks, I believe, and then we'll bid everyone farewell and thanks for attending. So Andrew, if you want to take it away.
Yeah, I mean, since we're a little bit over time anyway, I'm going to keep things as brief as I can. I just want to note this has been a great session with lots of really interesting talks, like perception and state estimation methods that are robust to visual and other challenges. As we've seen, are pretty essential to autonomous field robots to be useful in any environment, and it's good to see in this workshop that there's a wealth of very, very exciting work going on in that field. I just want to thank all of our speakers and all of the authors of our contributed papers who participated in the poster, air quotes, poster session, for their time and effort in helping make this workshop as interesting and useful as it was. I'd just like to very quickly note the talks that were presented today have been recorded and will be made available on the workshop's website, which is robustperception.net. The contributed papers are also going to be posted on the website. So if you happen to miss any component of this, you can go back and catch yourself up by visiting robustperception.net. And lastly, as may have been mentioned earlier, we're also considering a special journal issue on this workshop's topic, and we'll post any developments in that area to the website as well. So just thank you all once again for your time, attention, and contributions. I hope this has been a good start to the conference for you all.
Thank you again. Have a good afternoon, everybody.
Okay. Thank you for having us.
Thanks a lot. Thanks to the organizers.
Thank you. Bye-bye.
Bye-bye.